Subscribe to the channel so you don't miss out on any of these videos. Imagine a star so massive, so volatile, and so short-lived that its very existence defies everything we thought we knew about the cosmos. These are Wolf-Rayet stars, celestial titans burning so fiercely that they rip themselves apart, shedding their outer layers into space in brilliant, violent displays of cosmic power. But these stars don't just burn brightly. They are harbingers of chaos and creation, heralding the end of their lives with cataclysmic events that can outshine entire galaxies. What makes these stars so rare, so mysterious, and so important in the grand cosmic tapestry? And what secrets do they hold about the fate of our universe? Stay with me as we unravel the enigma of Wolf-Rayet stars, the ticking time bombs of the cosmos. To understand what makes Wolf-Rayet stars so extraordinary, let's first grasp what they are. These stars are massive, far more massive than our Sun, often ranging between 20 and 50 times its mass. Unlike ordinary stars, Wolf-Rayet stars are in a constant state of shedding, losing vast amounts of their outer material through intense stellar winds that can reach millions of miles per hour. This process leaves their dense, hot cores exposed, creating a spectacle of ultraviolet radiation and high-energy particles. These stars are a rare sight, accounting for only a tiny fraction of all stars in the universe, and they exist in a state of perpetual instability, teetering on the brink of destruction. The origins of Wolf-Rayet stars are as fascinating as their eventual demise. They form from massive stars that are nearing the end of their hydrogen-burning phase. When the hydrogen in the star's core is depleted, fusion slows down, and the balance between gravity and radiation pressure is disrupted. For most stars, this would lead to a relatively calm expansion into a red giant phase. But for the behemoths destined to become Wolf-Rayet stars, the story takes a different turn. The intense heat and pressure in their cores ignite the fusion of heavier elements like helium, carbon, and even oxygen, leading to an explosive increase in energy output. This energy fuels the powerful stellar winds that strip away the star's outer layers, exposing the hot, luminous core beneath. But why do Wolf-Rayet stars shed their outer layers so aggressively? The answer lies in their immense mass and temperature. These stars are so hot, often exceeding 50,000 Kelvin, that their radiation pressure is strong enough to overcome the star's gravitational pull. This creates a relentless outflow of material, with the star losing mass at an astonishing rate. In just a few 100,000 years, a Wolf-Rayet star can shed more than half its original mass, spewing it into space in the form of high-speed winds. This material, rich in elements like carbon, oxygen, and nitrogen, seeds the surrounding interstellar medium, contributing to the formation of new stars and planets. The role of Wolf-Rayet stars in the cosmic ecosystem cannot be overstated. These stars are among the universe's most efficient factories for producing heavy elements. The material they eject forms the building blocks of life as we know it. Every atom of carbon in your body, every molecule of oxygen you breathe, and even the calcium in your bones were forged in the fiery hearts of stars like these. But their contribution to the cosmos doesn't end there. The stellar winds of Wolf-Rayet stars can trigger the formation of new stars in nearby clouds of gas and dust, setting off a chain reaction of cosmic creation that shapes entire galaxies. As Wolf-Rayet stars near the end of their lives, they become even more enigmatic. Their cores, now stripped of their outer layers, are composed of exotic materials like neon and magnesium, fusing heavier and heavier elements in a desperate attempt to stave off collapse. But this process cannot continue indefinitely. Once the core begins fusing iron, the star reaches a critical point. Fusion can no longer generate enough energy to counteract gravity, and the core collapses in a fraction of a second. What happens next depends on the star's remaining mass. For many Wolf-Rayet stars, this collapse triggers a supernova explosion, a cataclysmic event that releases more energy in a few seconds than our Sun will produce in its entire lifetime. The explosion ejects the star's outer layers into space at incredible speeds, creating spectacular nebulae, and leaving behind either a neutron star or a black hole. In some cases, the collapse is so complete that the entire core becomes a black hole, a region of space where gravity is so strong that not even light can escape. But not all Wolf-Rayet stars end their lives as supernovae. Some may collapse directly into black holes without a visible explosion, a phenomenon known as a failed supernova. These events are harder to detect but no less important, as they provide crucial insights into the life cycles of massive stars and the formation of black holes. One of the most fascinating aspects of Wolf-Rayet stars is their role in producing gamma-ray bursts, intense beams of high-energy radiation that are among the most powerful events in the universe. When a Wolf-Rayet star collapses into a black hole, it can generate twin jets of gamma rays that shoot out from its poles at nearly the speed of light. These bursts can last from a few milliseconds to several minutes, and are so bright that they can be detected across billions of light years. Gamma-ray bursts are rare but incredibly significant, as they can reveal information about the early universe and the processes that shape galaxies. Despite their importance, much about Wolf-Rayet stars remains shrouded in mystery. How do they form so quickly, and why are they so rare? What determines whether a Wolf-Rayet star will end its life as a supernova, a gamma-ray burst, or a direct collapse into a black hole? And could the intense radiation and particle winds from these stars have implications for life on planets in their vicinity? These are questions that astronomers are only beginning to explore, using advanced telescopes and computational models to unravel the complexities of these stellar giants. Wolf-Rayet stars also challenge our understanding of the limits of star formation and stability. Their immense mass and luminosity push the boundaries of what we thought stars could achieve, raising questions about the processes that govern their birth and evolution. Some theories suggest that Wolf-Rayet stars could be the progenitors of even more massive objects, like parent stability supernovae or hypernovae, which release unprecedented amounts of energy and reshape their surrounding environments. The environments surrounding Wolf-Rayet stars are as fascinating as the stars themselves. The intense winds and radiation from these giants create massive bubbles in the interstellar medium, known as Wolf-Rayet nebulae. These nebulae are formed when the fast-moving stellar winds collide with the slower-moving material ejected during the earlier phases of the star's life. This interaction generates shockwaves that heat the gas to millions of degrees, causing it to emit X-rays and glow in a variety of colors. Observing these nebulae provides astronomers with valuable clues about the history and evolution of the Wolf-Rayet star at their center. Interestingly, the study of Wolf-Rayet stars also intersects with the search for cosmic origins. The elements ejected by these stars enrich the interstellar medium, contributing to the chemical diversity of the universe. When this material eventually condenses to form new stars and planets, it carries the fingerprints of its stellar predecessors. This process is a vital link in the cosmic chain of creation, demonstrating how the life and death of stars shape the universe on every scale, from the smallest dust particle to the largest galaxy. Wolf-Rayet stars also offer a unique window into the early universe. These stars are thought to be similar in many ways to the first generation of stars that formed after the Big Bang, known as population 3 stars. While no population 3 stars have been observed directly, their extreme temperatures, high masses, and short lifespans are believed to resemble those of modern Wolf-Rayet stars. By studying Wolf-Rayet stars, astronomers can gain indirect insights into the processes that dominated the early universe, including the formation of the first black holes and the reionization of the cosmos. Another intriguing aspect of Wolf-Rayet stars is their potential connection to the mysterious phenomenon of superluminous supernovae. These are explosions that are far brighter than typical supernovae, often outshining their entire host galaxies. While the exact mechanisms behind superluminous supernovae are still debated, some theories suggest that Wolf-Rayet stars could be responsible. Their high masses and stripped-down cores make them prime candidates for producing the conditions necessary for these extraordinary explosions. Observing superluminous supernovae and tracing them back to their progenitor stars could unlock new understanding about the limits of stellar evolution. The rarity of Wolf-Rayet stars adds another layer of fascination. These stars are not evenly distributed throughout the universe but are often found in regions of intense star formation, such as spiral arms of galaxies or starburst regions. Their scarcity is due in part to their short lifespans, which can be as brief as a few 100,000 years, a blink of an eye in cosmic terms. This means that at any given time, there are relatively few Wolf-Rayet stars visible in the night sky, making each one a precious opportunity for study. Observing Wolf-Rayet stars is no simple task. Their intense brightness and high-energy emissions make them stand out, but their distance from Earth and the dense clouds of gas and dust that often surround them can complicate observations. Astronomers use a variety of tools to study these stars, including optical telescopes to capture their light, X-ray telescopes to observe their high-energy emissions, and radio telescopes to map the structure of their stellar winds and surrounding nebulae. The data collected from these observations are then fed into complex models that simulate the life cycles of these stars, helping researchers predict their behavior and outcomes. Despite these efforts, many questions remain unanswered. For instance, why do some Wolf-Rayet stars produce gamma-ray bursts while others do not? What role do magnetic fields play in shaping the evolution and final outcomes of these stars? And how do Wolf-Rayet stars interact with their environments on a larger scale, influencing the dynamics of their host galaxies? These are active areas of research, and each new discovery brings us closer to understanding these enigmatic celestial giants. One of the most exciting developments in the study of Wolf-Rayet stars is the use of gravitational wave observatories. These instruments, such as LIGO and Virgo, have revolutionized our ability to detect the ripples in spacetime caused by the collisions of massive objects like black holes and neutron stars. Some of these collisions are thought to originate from binary systems involving Wolf-Rayet stars. By studying the gravitational waves produced by these events, scientists can gain new insights into the final stages of Wolf-Rayet stars and the formation of compact objects. Wolf-Rayet stars also play a role in the search for extraterrestrial life. While the intense radiation and stellar winds from these stars make their immediate environments inhospitable, the heavy elements they produce are essential for life as we know it. Understanding the distribution and abundance of these elements in the galaxy can help researchers identify regions that may be more likely to host habitable planets. Additionally, the nebulae formed by Wolf-Rayet stars could provide unique conditions for the formation of complex organic molecules, offering another avenue for studying the origins of life. The fate of Wolf-Rayet stars is a poignant reminder of the transient nature of even the most powerful objects in the universe. These stars, which burn so brightly and live so dramatically, ultimately meet their end in spectacular fashion, leaving behind remnants that continue to influence the cosmos for billions of years. Whether they end as neutron stars, black holes, or something even more exotic, their legacy is etched into the very fabric of the universe. As we gaze up at the night sky, it's humbling to think about the forces at work in the universe, the cycles of creation and destruction, the interplay of light and matter, and the relentless march of time that governs the lives of stars and galaxies. Wolf-Rayet stars are a testament to the incredible diversity and complexity of the cosmos, offering a glimpse into the processes that shape our universe on the grandest scales. By studying these enigmatic giants, we not only learn more about the stars themselves but also about our place in the vast, interconnected web of existence. The study of Wolf-Rayet stars is as much a testament to human curiosity as it is a scientific endeavor. These stars, though rare and fleeting, represent the pinnacle of stellar evolution in many ways. Their extreme characteristics push the boundaries of what we understand about the life cycle of stars, the chemistry of the universe, and even the limits of physics itself. Each new discovery about these stellar giants peels back another layer of mystery, but often reveals more questions than answers. Take, for example, the role of rotation in Wolf-Rayet stars. Rapid rotation can lead to significant distortions in the star's shape, causing it to bulge at the equator and flatten at the poles. This rotational phenomenon also influences the distribution of the star's winds and the outflow of material. Fast rotation may even lead to the formation of polar jets, streams of particles ejected at nearly the speed of light from the star's poles. These jets, while theoretically predicted, are still poorly understood and are a major focus of observational astronomy. The interplay between rotation, magnetic fields, and mass loss creates a dynamic and chaotic environment around Wolf-Rayet stars. Magnetic fields, in particular, play a crucial but enigmatic role in shaping the evolution of these stars. Observations suggest that some Wolf-Rayet stars possess strong magnetic fields, which can channel the flow of stellar winds and create complex structures in their surrounding nebulae. These magnetic fields may also influence the way the star collapses, potentially altering the nature of the resulting supernova or black hole. Speaking of black holes, the relationship between Wolf-Rayet stars and black holes is one of the most compelling aspects of modern astrophysics. Not all Wolf-Rayet stars end their lives as black holes. Some collapse into neutron stars, while others might explode as unbound supernovae that leave no compact remnant. The determining factors include the star's mass, composition, and the rate at which it loses material during its lifetime. Studying Wolf-Rayet stars helps scientists refine their models of stellar evolution and better predict the conditions under which black holes form. These connections between Wolf-Rayet stars and black holes also tie into the mysterious phenomenon of gamma-ray bursts. These are some of the most energetic events in the universe, releasing more energy in a few seconds than the Sun will emit in its entire lifetime. Long-duration gamma-ray bursts, in particular, are thought to originate from the collapse of massive stars, including Wolf-Rayet stars. The exact mechanisms that produce these bursts remain elusive, but they likely involve the rapid rotation and intense magnetic fields that characterize these stellar giants. By studying Wolf-Rayet stars, astronomers hope to uncover the secrets behind these cosmic fireworks. Wolf-Rayet stars are also intrinsically tied to the concept of cosmic alchemy. As they shed their outer layers, they distribute elements like carbon, oxygen, and nitrogen into the surrounding space. These elements, forged in the nuclear furnaces of the star's cores, are the building blocks of planets, oceans, and even life itself. Without the contributions of stars like these, the universe would lack the chemical diversity necessary for complex structures and organisms to exist. In this sense, Wolf-Rayet stars are not just destructive forces. They are also creators, seeding the cosmos with the ingredients for new generations of stars and planets. The environments around Wolf-Rayet stars are equally fascinating. The intense stellar winds carve out intricate structures in the surrounding interstellar medium, creating nebulae that are as beautiful as they are scientifically significant. These nebulae can take on a variety of shapes, from spherical shells to complex, filamentary patterns, depending on the dynamics of the winds and the properties of the surrounding material. Observing these nebulae provides a window into the processes that govern stellar wind interactions, shockwave formation, and the recycling of material in galaxies. One of the most striking features of Wolf-Rayet nebulae is their ability to emit X-rays, a testament to the high-energy processes occurring within them. These X-rays are produced when the fast-moving stellar winds collide with slower-moving material, creating shockwaves that heat the gas to millions of degrees. The resulting emissions provide crucial data about the temperature, density, and composition of the gas, offering insights into the physical conditions around the star. Advanced telescopes like the Chandra X-ray Observatory and the James Webb Space Telescope are helping astronomers study these emissions in unprecedented detail. The sheer power of Wolf-Rayet stars also has implications for their surrounding environments on larger scales. The intense radiation and stellar winds from these stars can trigger or inhibit star formation in nearby regions. In some cases, the winds compress clouds of gas and dust, causing them to collapse and form new stars. In other cases, the winds may disperse these clouds, preventing star formation altogether. This dual role makes Wolf-Rayet stars key players in the ongoing evolution of galaxies, influencing the birth and death of stars over cosmic timescales. Despite their immense luminosity and dramatic behavior, Wolf-Rayet stars remain elusive targets for observation. They are rare, comprising only a tiny fraction of all stars in the universe, and their short lifespans make them fleeting phenomena. Most of them are located in distant regions of the galaxy, often obscured by clouds of gas and dust. Advances in telescope technology, however, are making it possible to study these stars in greater detail. Instruments capable of detecting infrared and X-ray emissions are particularly useful, as they can penetrate the dense material surrounding these stars and reveal their inner workings. One of the most exciting frontiers in the study of Wolf-Rayet stars is the use of gravitational waves to probe their final moments. When a Wolf-Rayet star collapses to form a black hole or neutron star, the event can produce ripples in spacetime that are detectable by instruments like LIGO and Virgo. These gravitational waves carry information about the mass, spin, and other properties of the collapsing star, offering a new way to study these enigmatic objects. Future observatories, such as the planned LISA mission, promise to extend this capability even further, allowing scientists to detect gravitational waves from even more distant and exotic systems. As research into Wolf-Rayet stars continues, it becomes increasingly clear that these stellar giants are more than just isolated phenomena. They are integral to the larger story of the universe. From their role in the chemical evolution of galaxies to their connections with black holes and gamma-ray bursts, Wolf-Rayet stars are a cornerstone of modern astrophysics. They challenge our understanding of the cosmos and inspire us to look deeper into the night sky, seeking answers to the questions they pose. The fascination with Wolf-Rayet stars goes beyond their immediate impact on astrophysics and delves into their role as cosmic storytellers. Each Wolf-Rayet star is a snapshot of a specific moment in stellar evolution, a fleeting chapter in the life cycle of some of the most massive stars in existence. Their existence is a testament to the forces that shape the cosmos, from the delicate interplay of nuclear fusion and gravity to the dynamic processes that govern the distribution of matter and energy across galaxies. One of the lesser-known but equally intriguing aspects of Wolf-Rayet stars is their variability. Despite their massive and seemingly stable exteriors, these stars often experience dramatic changes in brightness and spectral characteristics. This variability is driven by multiple factors, including pulsations in the star's outer layers, changes in mass loss rates, and interactions with companion stars and binary systems. These fluctuations provide valuable clues about the internal processes occurring within these stars, allowing astronomers to refine models of their behavior. In binary systems, Wolf-Rayet stars are particularly fascinating. When paired with a massive companion, the interaction between the two stars creates a dynamic and often chaotic environment. The stellar winds from the Wolf-Rayet star collide with those from its companion, generating shock fronts that produce intense X-ray emissions. These collisions can also lead to the formation of complex structures, such as spiral patterns in the circumstellar material. Observing these systems offers a unique opportunity to study the effects of stellar wind interactions and the role of binaries in stellar evolution. Some binary systems containing Wolf-Rayet stars are considered progenitors of gravitational wave events. When the two stars are massive enough and in close orbit, their eventual collapse can lead to the formation of a binary black hole or a neutron-star black hole pair. The merger of these compact objects produces gravitational waves that can be detected across vast distances, providing a direct link between Wolf-Rayet stars and the cutting-edge field of gravitational wave astronomy. Understanding these systems helps scientists trace the origins of gravitational wave sources and unravel the complex history of massive stars. The winds of Wolf-Rayet stars are also a topic of ongoing investigation. These winds are not uniform but rather clumpy and inhomogeneous, with dense regions of material interspersed with less dense zones. This clumpiness affects how the wind interacts with its surroundings, influencing the formation of shockwaves, the creation of nebulae, and the distribution of enriched material in the interstellar medium. Advanced computational models and high-resolution observations are helping researchers uncover the mechanisms that drive this clumpiness and its implications for the evolution of these stars. The intense radiation emitted by Wolf-Rayet stars also plays a role in shaping their surroundings. This radiation ionizes nearby gas, creating regions of hot, ionized plasma that emit light in a range of wavelengths. These ionized regions, known as H2 regions, are often associated with star-forming regions in galaxies. Studying the interaction between Wolf-Rayet stars and their surrounding H2 regions provides insights into the processes that govern star formation and the life cycle of interstellar matter. Wolf-Rayet stars are also thought to play a role in the evolution of galaxies on a larger scale. Their powerful winds and supernova explosions inject energy into the interstellar medium, driving turbulence and shaping the structure of galaxies. In some cases, this feedback can trigger the formation of new stars by compressing clouds of gas and dust. In others, it may inhibit star formation by dispersing these clouds. This dual role makes Wolf-Rayet stars key players in the ongoing evolution of galaxies, influencing the distribution of matter and the pace of star formation over cosmic timescales. The study of Wolf-Rayet stars has also benefited from the advent of multi-messenger astronomy, which combines observations across different types of signals, including light, gravitational waves, and neutrinos. Neutrinos, for instance, are nearly massless particles that are produced in enormous quantities during supernova explosions and other high-energy events. Detecting neutrinos from a Wolf-Rayet progenitor could provide direct evidence of the processes occurring in the star's core, offering a new way to study these elusive objects. Despite their rarity, Wolf-Rayet stars are increasingly becoming the focus of observational campaigns aimed at understanding the most extreme phenomena in the universe. Advanced telescopes, such as the Extremely Large Telescope, ELT, and the Square Kilometre Array, SKA, promise to revolutionize our ability to study these stars in detail. These instruments will allow astronomers to observe Wolf-Rayet stars in distant galaxies, providing a broader perspective on their role in the cosmos. The future of Wolf-Rayet research is also tied to the study of their ultimate fate. As these stars approach the end of their lives, they undergo a series of dramatic changes that culminate in their collapse. Understanding these final stages is crucial for predicting the nature of the resulting supernova or black hole. Recent observations have identified potential pre-supernova signatures in some Wolf-Rayet stars, such as sudden increases in brightness or changes in their spectral characteristics. Monitoring these stars in real time could provide the first direct evidence of a star transitioning from a Wolf-Rayet phase to a supernova. One of the most enigmatic aspects of Wolf-Rayet stars is their role in the formation of long-duration gamma-ray bursts, GRBs. These bursts, which are among the most energetic events in the universe, are thought to occur when a massive star collapses to form a black hole. The rotational energy of the collapsing star powers a relativistic jet, which emits intense gamma rays. Observations suggest that some Wolf-Rayet stars have the necessary conditions, high mass, rapid rotation, and a stripped envelope, to produce GRBs. By studying these stars, astronomers hope to uncover the mechanisms that drive these extraordinary events. The connection between Wolf-Rayet stars and cosmic ray production is another area of active research. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, originating from a variety of sources, including supernovae and black holes. The intense winds and shockwaves associated with Wolf-Rayet stars may accelerate particles to the extreme energies required for cosmic rays. Understanding this process could shed light on one of the most enduring mysteries of astrophysics: the origin of cosmic rays and their impact on the universe. The quest to understand Wolf-Rayet stars is a testament to the power of human curiosity and ingenuity. These stars, with their immense luminosity, powerful winds, and fleeting lifespans, challenge our understanding of the universe and inspire us to explore new frontiers in science. As we continue to study these stellar giants, we are not only uncovering the secrets of their lives but also gaining a deeper appreciation for the complexity and beauty of the cosmos. The enduring mystery of Wolf-Rayet stars lies in their complexity and their influence across multiple domains of astrophysics. These stellar giants, teetering on the brink of collapse, represent both an end and a beginning, a transition from the luminous lives of massive stars to the explosive phenomena that reshape galaxies. They are the architects of cosmic events, enriching the universe with heavy elements, sculpting the interstellar medium, and paving the way for new generations of stars and planetary systems. One of the most exciting questions surrounding Wolf-Rayet stars concerns their internal dynamics, especially as they approach the end of their lives. What happens deep within the cores of these stars as they run out of nuclear fuel? Current models suggest that the core contracts under its own gravity, growing hotter and denser until it can no longer support itself. The exact mechanism of this collapse depends on several factors, including the star's mass, composition, and rotation rate. In some cases, the collapse leads to a supernova, where the outer layers of the star are ejected in a violent explosion. In others, the core may form a black hole or a neutron star, with little or no visible explosion. The diversity of outcomes is tied to the initial mass and metallicity of the Wolf-Rayet star. Stars in regions with low metallicity, such as early galaxies, may retain more of their mass throughout their lives, leading to different evolutionary paths. These low-metallicity Wolf-Rayet stars are of particular interest because they resemble the first-generation stars that formed in the early universe. By studying them, astronomers can gain insights into the processes that shaped the earliest galaxies and set the stage for cosmic evolution. Another layer of complexity arises from the role of magnetic fields in Wolf-Rayet stars. Although these stars are known for their strong stellar winds and high mass loss rates, the influence of magnetic fields on these processes is not yet fully understood. Magnetic fields can channel and accelerate stellar winds, creating intricate patterns in the circumstellar material. They may also influence the rotation of the star, which is a critical factor in determining its fate. Advanced spectroscopic techniques and polarimetric observations are helping scientists probe the magnetic properties of Wolf-Rayet stars, revealing new details about their internal and external dynamics. The interplay between Wolf-Rayet stars and their surroundings extends to their interactions with interstellar dust. While these stars are primarily known for their winds and ionizing radiation, they also play a role in the formation and destruction of dust in the galaxy. Observations have shown that the winds of Wolf-Rayet stars can condense certain elements into tiny solid grains, contributing to the galaxy's dust budget. However, the intense radiation from these stars can also destroy existing dust, creating a complex feedback loop that shapes the interstellar environment. Understanding this balance is crucial for piecing together the life cycle of matter in the universe. In recent years, astronomers have discovered Wolf-Rayet stars in environments that challenge our understanding of their formation and evolution. For example, some have been found in star clusters with ages that suggest they should not yet exist, given the time it takes for massive stars to evolve into the Wolf-Rayet phase. These premature Wolf-Rayet stars may have formed through alternative pathways, such as stellar mergers or the stripping of mass from a companion star in a binary system. These discoveries are reshaping our understanding of the diversity of stellar evolution pathways and the factors that influence the lives of massive stars. Wolf-Rayet stars also serve as laboratories for studying the interplay between nuclear physics and astrophysics. The extreme conditions in their cores, temperatures of millions of degrees and densities billions of times that of water, drive nuclear reactions that cannot be replicated on Earth. These reactions produce elements such as oxygen, carbon, and neon, which are later expelled into space during the star's death throes. By studying the light emitted by Wolf-Rayet stars, astronomers can identify the signatures of these nuclear processes and refine their models of stellar nucleosynthesis. The final moments of a Wolf-Rayet star's life are among the most dramatic events in the cosmos. As the star exhausts its nuclear fuel, the core contracts, and the outer layers are ejected at tremendous speeds. The resulting supernova explosion releases an enormous amount of energy, lighting up the surrounding space and triggering the formation of new stars. In cases where the core forms a black hole, the collapse can generate jets of material that travel at nearly the speed of light, producing phenomena such as gamma-ray bursts. Observing these events in real time is a major goal of modern astronomy, as it offers a unique opportunity to study the physics of extreme conditions. Wolf-Rayet stars also provide clues about the environments in which they formed. By analyzing the composition of their winds and their surrounding nebulae, scientists can infer the properties of the molecular clouds from which these stars originated. This information is vital for understanding the conditions that lead to the formation of massive stars and the factors that influence their early evolution. It also helps astronomers piece together the history of star formation in different regions of the galaxy. One of the most intriguing questions about Wolf-Rayet stars is their role in the cosmic cycle of matter and energy. These stars are not isolated objects but are deeply interconnected with the galaxies they inhabit. Their winds and supernova explosions inject energy into the interstellar medium, driving turbulence and mixing elements throughout the galaxy. This feedback influences the rate of star formation, the distribution of matter, and the evolution of galaxies over cosmic timescales. By studying Wolf-Rayet stars, we are not only learning about the lives of individual stars but also gaining a broader understanding of the processes that shape the universe. Despite decades of study, Wolf-Rayet stars remain enigmatic, with many unanswered questions about their formation, evolution, and ultimate fate. Their rarity and short lifespans make them challenging to observe, but advances in technology are opening new windows into their secrets. From space-based telescopes like the James Webb Space Telescope to ground-based observatories equipped with adaptive optics, astronomers are gaining unprecedented insights into these cosmic giants. As we continue to explore their mysteries, Wolf-Rayet stars promise to reveal new layers of complexity and beauty in the universe. The journey of understanding Wolf-Rayet stars is far from complete, as each discovery raises new questions that compel us to look deeper into the nature of these stellar giants. One of the most captivating aspects of these stars is their role as cosmic catalysts. Their existence is a reminder of how intertwined everything in the universe is, from the tiniest particles to the grandest cosmic structures. As these stars shed their outer layers, they leave behind glowing shells of ionized gas, known as Wolf-Rayet nebulae. These nebulae serve as archives of the star's life, preserving clues about its evolution, mass loss history, and interactions with the interstellar medium. Detailed observations of these nebulae reveal stunningly intricate structures, from spherical shells to complex, asymmetrical shapes. These formations are sculpted by the interplay between the star's winds, magnetic fields, and surrounding material. Advanced imaging techniques, such as those employed by the Hubble Space Telescope, have allowed astronomers to study these nebulae in extraordinary detail, unveiling patterns and processes that were previously hidden. Wolf-Rayet nebulae are not only visually striking but also scientifically invaluable. By analyzing the light they emit, scientists can determine the chemical composition of the ejected material, providing direct evidence of the nuclear reactions that occurred within the star. These studies have confirmed that Wolf-Rayet stars are major contributors to the cosmic abundance of certain elements, such as carbon, nitrogen, and oxygen. These elements are essential for the formation of planets and life, linking the fates of these massive stars to the broader story of cosmic evolution. Another layer of intrigue is the relationship between Wolf-Rayet stars and binary systems. A significant fraction of Wolf-Rayet stars are found in binaries, where they orbit a companion star. These systems offer a unique opportunity to study the effects of mass transfer and tidal interactions on stellar evolution. In some cases, the Wolf-Rayet star loses material to its companion, altering the evolutionary paths of both stars. In others, the two stars may merge, forming an even more massive and unstable star that rapidly evolves toward collapse. These binary interactions can also influence the types of explosions that occur when the stars reach the end of their lives, adding another layer of complexity to the puzzle of stellar death. One of the most exciting areas of research is the connection between Wolf-Rayet stars and gamma-ray bursts, GRBs. GRBs are among the most energetic events in the universe, releasing as much energy in a few seconds as the Sun will emit over its entire lifetime. They are thought to result from the collapse of a massive star's core, followed by the formation of a black hole or a rapidly spinning neutron star. Some models suggest that Wolf-Rayet stars are the progenitors of long-duration GRBs, which last more than 2 seconds and are associated with supernova explosions. Observations of GRBs often reveal the presence of heavy elements in the surrounding material, consistent with the idea that they originate from environments enriched by Wolf-Rayet stars. The study of Wolf-Rayet stars also intersects with the quest to understand black hole formation. These stars are among the most likely candidates to leave behind black holes when they die, particularly if they are massive enough to avoid a supernova explosion. The direct collapse of a Wolf-Rayet star into a black hole is thought to produce a distinct observational signature, including the absence of a visible explosion and the formation of relativistic jets. By identifying and studying such events, astronomers can refine their models of black hole formation and gain insights into the population of stellar mass black holes in the universe. The environments around Wolf-Rayet stars are also laboratories for studying cosmic ray acceleration. The strong winds and shocks produced by these stars can accelerate particles to near-light speeds, creating high-energy cosmic rays that permeate the galaxy. These cosmic rays play a crucial role in various astrophysical processes, from influencing the chemistry of interstellar clouds to triggering star formation. Understanding the mechanisms of cosmic ray acceleration in Wolf-Rayet systems could shed light on the broader role of these particles in shaping the universe. Wolf-Rayet stars are not just isolated phenomena, they are deeply embedded in the fabric of their host galaxies. Their intense radiation and winds can create cavities in the interstellar medium, known as wind-blown bubbles. These bubbles are often observed around Wolf-Rayet stars and provide a direct measure of their influence on their surroundings. By studying the size, shape, and composition of these bubbles, astronomers can learn about the energy output of Wolf-Rayet stars and their impact on the larger galactic ecosystem. The search for Wolf-Rayet stars has also expanded beyond the Milky Way to other galaxies, including those with very different environments. Observations of Wolf-Rayet stars in nearby galaxies, such as the Large and Small Magellanic Clouds, have revealed variations in their properties that reflect differences in metallicity and star formation history. These studies provide a broader context for understanding how Wolf-Rayet stars fit into the cosmic landscape and how their roles may vary across different regions of the universe. Despite their brightness and influence, Wolf-Rayet stars remain elusive in many ways. Their rarity means that only a few are close enough to study in detail, while their short lifespans make them fleeting in cosmic terms. New observational techniques, such as high-resolution spectroscopy and multi-wavelength imaging, are helping to overcome these challenges, providing more data than ever before. Instruments like the Very Large Telescope and the Atacama Large Millimeter/Submillimeter Array are pushing the boundaries of what we can observe, revealing new details about the lives and deaths of these extraordinary stars. Theoretical models have also advanced significantly, driven by the need to explain the complex phenomena associated with Wolf-Rayet stars. Computational simulations now incorporate a wide range of factors, from nuclear reactions and stellar winds to magnetic fields and binary interactions. These models are being tested and refined using data from observations, creating a feedback loop that drives progress in both theory and observation. As these models become more sophisticated, they are providing new insights into the fundamental physics of stars and the processes that govern their evolution. Ultimately, the study of Wolf-Rayet stars is a testament to the interconnectedness of the universe. These stars are not merely isolated objects, but are part of a vast cosmic web that links the smallest particles to the largest structures. By unraveling the mysteries of Wolf-Rayet stars, we are not only uncovering the secrets of stellar evolution but also gaining a deeper understanding of the universe as a whole. The allure of Wolf-Rayet stars lies in their multifaceted role in the cosmic narrative, bridging the life cycle of stars with the formation of the universe's most extreme objects. Their story doesn't end with their dramatic deaths. Instead, it marks the beginning of a ripple effect that influences galaxies, star clusters, and even planetary systems. To truly grasp the scope of their importance, we must dive deeper into the ongoing research, technological advancements, and the profound questions they continue to pose. One of the most intriguing areas of research involves the metallicity of Wolf-Rayet stars and how it affects their evolution and end states. Metallicity refers to the abundance of elements heavier than hydrogen and helium in a star, which plays a critical role in determining its mass loss and stability. Stars in low metallicity environments, such as those in the early universe, lose less mass through stellar winds, allowing them to retain more of their mass until the final stages of their lives. This difference has significant implications for the types of remnants they leave behind, whether they collapse into neutron stars, black holes, or something even more exotic. Studying low metallicity Wolf-Rayet stars is like peering back in time, offering a glimpse into the conditions that prevailed during the universe's infancy. Observations of distant galaxies with low metallicity reveal how these stars might have behaved billions of years ago, during the epoch when the first heavy elements were being forged in stellar interiors. By comparing these ancient stars to their modern counterparts, scientists can piece together a more comprehensive picture of stellar evolution across cosmic time. Another fascinating aspect of Wolf-Rayet stars is their role in shaping the interstellar medium, ISM. Their powerful winds and eventual supernova explosions inject enormous amounts of energy and enriched material into their surroundings, triggering shock waves that can compress nearby gas clouds and ignite new rounds of star formation. This process, known as positive feedback, highlights the cyclical nature of the cosmos, where the death of one generation of stars gives rise to the birth of another. Wolf-Rayet stars are particularly effective at this due to their high luminosities and intense winds, making them key players in the dynamic interplay between stars and the ISM. The interplay between Wolf-Rayet stars and the ISM also has implications for the formation of planetary systems. The heavy elements produced and distributed by these stars are essential building blocks for rocky planets, and, by extension, the potential for life. Studies of star-forming regions influenced by Wolf-Rayet winds have revealed intriguing connections between the properties of the ISM and the types of stars and planets that form within it. These findings suggest that Wolf-Rayet stars may play an indirect yet crucial role in shaping the conditions for habitability in the universe. One of the more speculative but fascinating questions surrounding Wolf-Rayet stars is their potential to harbor advanced civilizations. While their extreme environments are hostile to life as we know it, the regions they influence could provide fertile ground for the development of planetary systems with unique characteristics. For instance, the high levels of radiation and energetic particles in these regions could drive chemical reactions that lead to the formation of complex organic molecules, laying the groundwork for prebiotic chemistry. This idea remains highly theoretical, but it underscores the far-reaching impact of Wolf-Rayet stars on the broader question of life's origins and distribution in the cosmos. The technological advancements enabling these discoveries are as remarkable as the stars themselves. Instruments like the James Webb Space Telescope, JWST, and upcoming observatories like the Extremely Large Telescope, ELT, are poised to revolutionize our understanding of Wolf-Rayet stars. These cutting-edge tools provide unprecedented sensitivity and resolution, allowing astronomers to probe deeper into the physical processes that govern these stars. From studying the intricacies of their winds to mapping their environments in 3 dimensions, these technologies are opening new frontiers in astrophysics. Computational astrophysics is another area experiencing rapid growth, fueled by the increasing power of supercomputers. Simulating the evolution of Wolf-Rayet stars and their interactions with their surroundings requires solving complex equations that account for everything from nuclear fusion to radiative transfer. These simulations are becoming increasingly realistic, providing valuable insights into phenomena that are difficult or impossible to observe directly. For example, models of binary Wolf-Rayet systems have revealed how mass transfer and orbital dynamics can lead to exotic outcomes, such as the formation of hypervelocity stars or the ejection of massive stars from their host galaxies. The connection between Wolf-Rayet stars and gravitational waves is yet another frontier of discovery. When 2 massive stars in a binary system end their lives as black holes or neutron stars, their merger can produce gravitational waves, ripples in the fabric of spacetime that can be detected by observatories like LIGO and Virgo. These detections provide a new way to study the final stages of Wolf-Rayet stars, offering insights into their masses, spins, and the environments in which they form. As gravitational wave astronomy continues to mature, it promises to shed light on the mysterious lives and deaths of these cosmic giants. Despite all we have learned, many questions about Wolf-Rayet stars remain unanswered. What determines the precise conditions under which they explode as supernovae or collapse directly into black holes? How do their winds interact with magnetic fields? And what role do these fields play in shaping their evolution? What are the mechanisms behind the formation of the complex nebulae that surround them? And what can these structures tell us about the history of these stars? These are just a few of the mysteries that continue to drive research in this field. The study of Wolf-Rayet stars is not just about understanding these specific objects. It is about exploring the fundamental processes that govern the universe. From the synthesis of elements to the formation of black holes, these stars touch on some of the most profound questions in astrophysics. Their story is a reminder that even in the vastness of the cosmos, every piece fits into a larger puzzle, and every discovery brings us one step closer to understanding our place in the universe. Wolf-Rayet stars exemplify the beauty and complexity of the cosmos. They are both creators and destroyers, their lives marked by extremes that challenge our understanding and inspire our imagination. As we continue to study these stellar giants, we are not just uncovering the secrets of their existence. We are also gaining a deeper appreciation for the interconnectedness of all things. Whether as sources of light and elements, progenitors of black holes, or agents of cosmic transformation, Wolf-Rayet stars remind us of the dynamic and ever-evolving nature of the universe we call home. The influence of Wolf-Rayet stars extends beyond their immediate environments, shaping entire regions of galaxies and, in some cases, influencing the broader structure of the cosmos. These stars represent a bridge between the observable and the theoretical, offering scientists the chance to test models of stellar evolution, supernova mechanics, and black hole formation against real-world observations. As such, they serve as laboratories for some of the most fundamental questions in astrophysics. One particularly fascinating topic is how Wolf-Rayet stars interact with their galactic neighborhoods. Their strong stellar winds not only enrich the interstellar medium but also carve out vast, bubble-like cavities known as Wolf-Rayet bubbles. These bubbles are shells of hot, ionized gas created when the winds from the star collide with surrounding material, compressing it into dense, often irregular structures. Observations of these bubbles provide valuable data on the energy output of Wolf-Rayet stars and the dynamics of their surroundings. The shapes and sizes of Wolf-Rayet bubbles can vary significantly depending on the star's environment. In dense star-forming regions, these bubbles may overlap and interact, creating complex networks of shock fronts that influence the birth of new stars. In more isolated areas, the bubbles expand relatively undisturbed, allowing researchers to study their internal structures and dynamics in greater detail. These observations help refine models of how energy and momentum are distributed in galactic ecosystems. One of the most visually stunning phenomena associated with Wolf-Rayet stars is the formation of intricate nebulae. The material expelled during the later stages of their lives often forms beautifully complex structures, ranging from circular halos to asymmetric filaments and knots. These nebulae serve as time capsules, preserving information about the star's mass loss history, chemical composition, and the interplay between stellar winds and surrounding gas. Observing and analyzing these nebulae gives scientists a window into the life cycles of massive stars and their contributions to the galactic environment. Advanced imaging techniques have allowed astronomers to capture unprecedented details of these nebulae. Instruments like the Hubble Space Telescope and the Atacama Large Millimeter/Submillimeter Array (ALMA) provide high-resolution views that reveal the interplay between various physical processes. For example, researchers have discovered that magnetic fields play a significant role in shaping the morphology of these nebulae, influencing the flow of material and creating patterns that would otherwise be difficult to explain. Another area of growing interest is the role of Wolf-Rayet stars in the formation of long-duration gamma-ray bursts, GRBs. These bursts are some of the most energetic events in the universe, releasing more energy in a few seconds than the Sun will emit over its entire lifetime. Observational evidence suggests that Wolf-Rayet stars are prime candidates for the progenitors of these bursts, particularly in cases where the star collapses directly into a black hole. The connection between Wolf-Rayet stars and GRBs lies in their rotational properties and the composition of their outer layers. Rapidly rotating Wolf-Rayet stars with stripped hydrogen envelopes are thought to be ideal candidates for GRB production. When such a star collapses, its rotational energy powers a relativistic jet that pierces through the stellar material, generating the gamma-ray emission we detect. These events provide crucial data for understanding both the mechanics of stellar collapse and the conditions required for jet formation. Studying GRBs associated with Wolf-Rayet stars also offers insights into the distant universe. Because GRBs are so luminous, they can be observed at extreme cosmological distances, effectively serving as beacons that illuminate the early stages of galaxy formation. By analyzing the light from these bursts, scientists can study the chemical composition and physical properties of gas clouds in the early universe, providing a unique perspective on how the first generations of stars and galaxies evolved. Despite these advances, many mysteries remain. For instance, the exact mechanisms that determine whether a Wolf-Rayet star explodes as a supernova or collapses directly into a black hole are not fully understood. Current models suggest that factors like mass, rotation, and metallicity play critical roles, but disentangling their relative contributions remains a significant challenge. Observations of nearby Wolf-Rayet stars, combined with theoretical modeling, are helping to address these questions, but much work remains to be done. Another intriguing mystery involves the relationship between Wolf-Rayet stars and binary systems. A significant fraction of these stars are found in binary or multiple star systems, where their interactions can lead to unique and often dramatic outcomes. Mass transfer between companions can strip one star of its outer layers, creating conditions for exotic phenomena like type Ia supernovae, X-ray binaries, or even double black hole mergers. These systems are natural laboratories for studying the interplay between stellar evolution and gravitational dynamics. Recent discoveries of Wolf-Rayet stars and binary systems have also shed light on the role of tidal forces in shaping their evolution. Tidal interactions can influence the rotational speeds of the stars, altering their mass loss rates and chemical mixing. In some cases, these interactions can lead to the synchronization of the star's orbits and spins, creating conditions that are ripe for the production of gravitational waves. As observational techniques improve, more such systems are being identified, offering new opportunities to study these complex dynamics. The contribution of Wolf-Rayet stars to galactic evolution cannot be overstated. Their massive outflows of material enrich the interstellar medium with heavy elements, providing the raw materials for future generations of stars and planets. These stars are also responsible for creating some of the most spectacular structures in the universe, from nebulae to supernova remnants, each of which serves as a monument to the transformative power of stellar evolution. Yet, even as we uncover more about these enigmatic stars, they continue to challenge our understanding of the cosmos. Their extreme properties push the boundaries of what is physically possible, forcing scientists to refine theories and develop new models. They are a testament to the complexity and beauty of the universe, reminding us that even the most massive and luminous stars are part of a larger, interconnected system. As we stand on the brink of new discoveries, the study of Wolf-Rayet stars promises to yield even more profound insights into the nature of the universe. From their origins in star-forming regions to their final moments as supernovae or black holes, these stars encapsulate the grandeur and mystery of the cosmos. They are not just objects of scientific inquiry but also sources of wonder and inspiration, inviting us to look deeper into the night sky and ponder our place in the grand tapestry of existence. As we continue to investigate the mysteries surrounding Wolf-Rayet stars, it's essential to address some of the more intricate questions that remain unanswered. One of these is the exact origin of their remarkable mass loss rates. While it is widely accepted that their intense stellar winds are responsible for stripping away their outer layers, the mechanisms driving these winds are still a subject of ongoing research. In the past, it was believed that radiation pressure alone, caused by the energy emitted by the star's surface, was sufficient to drive these massive winds. However, newer models suggest that additional factors, such as instabilities in the star's outer layers or magnetic fields, may also play crucial roles in accelerating the gas to such high velocities. These winds can reach speeds of up to 3,000 km per second, ejecting material into space that will eventually become part of the galactic interstellar medium. Understanding the full range of forces involved in this process could offer new insights into the dynamics of massive stars and their evolution. Moreover, the chemical composition of Wolf-Rayet stars and their surroundings adds another layer of complexity to their study. As these stars shed their outer layers, they release a rich mixture of elements into the surrounding gas. This material, which includes elements like carbon, oxygen, nitrogen, and helium, is crucial for the formation of future stars, planets, and even life as we know it. The chemical enrichment provided by Wolf-Rayet stars helps shape the evolution of galaxies, contributing to the cosmic recycling process that fuels the birth of new generations of stars. However, not all of the elements released by these stars are benign. Wolf-Rayet stars are also responsible for producing heavier elements, such as gold, platinum, and uranium, through processes like the R process, rapid neutron capture. These elements are thought to play a significant role in the formation of neutron stars and black holes, where the extreme conditions allow for the synthesis of even heavier elements. The birth and eventual death of a Wolf-Rayet star thus marks a pivotal moment in the life cycle of galaxies, as it contributes both to the creation of the building blocks for new stars and the formation of exotic objects like black holes. Another fascinating aspect of Wolf-Rayet stars is their potential role in triggering star formation. The intense radiation and stellar winds from these stars can compress nearby gas clouds, creating the conditions necessary for the birth of new stars. This feedback mechanism is a critical component of the cycle of star formation and destruction in galaxies. Wolf-Rayet stars can act as both destroyers and creators, shaping the future of their galactic neighborhoods through their explosive death throes and massive outflows of material. In addition to their role in star formation, Wolf-Rayet stars are often found in regions of intense cosmic activity, such as starburst galaxies. These galaxies, which experience rapid bursts of star formation, often host large numbers of Wolf-Rayet stars. The presence of these stars can help astronomers understand the processes that drive star formation in extreme environments. By studying the properties of Wolf-Rayet stars in these regions, scientists can gain valuable insights into the interplay between stellar evolution, galaxy formation, and the broader cosmic landscape. As we delve deeper into the study of Wolf-Rayet stars, the importance of multi-wavelength observations becomes increasingly apparent. While optical telescopes can provide stunning images of these stars and their surrounding nebulae, they offer only a partial view of the phenomena at play. To fully understand the behavior of these stars, astronomers rely on a wide range of observational techniques, including radio, infrared, and X-ray observations. These wavelengths allow researchers to probe the cooler, denser regions of the star's surroundings, as well as the high-energy processes that occur during their explosive deaths. One key aspect of this multi-wavelength approach is the study of Wolf-Rayet stars in different stages of their evolution. By observing these stars over time, scientists can track how their properties change as they shed their outer layers and approach the end of their lives. For example, some Wolf-Rayet stars exhibit peculiar variability, with their luminosity fluctuating over short periods. These variations may be caused by changes in the structure of the star's outer layers or the interaction of its winds with the surrounding gas. Understanding these fluctuations can provide valuable clues about the internal dynamics of the star and the forces at play in its final stages. The detection of Wolf-Rayet stars in distant galaxies is another exciting frontier in this field of study. These stars are incredibly rare, and their discovery in other galaxies allows astronomers to explore the conditions that exist in different regions of the universe. By studying the properties of Wolf-Rayet stars in distant galaxies, scientists can learn about the star formation history of these galaxies, their metallicity, and the impact of these stars on their surroundings. This research has the potential to revolutionize our understanding of galaxy evolution and the role of massive stars in shaping the universe. In the search for Wolf-Rayet stars, astronomers are increasingly turning to space-based telescopes. Instruments like the James Webb Space Telescope, with its advanced infrared capabilities, are capable of detecting the faint light emitted by these stars even at vast distances. This opens up new possibilities for studying Wolf-Rayet stars in the early universe, providing insights into the conditions that existed when the first galaxies formed. The potential for groundbreaking discoveries in this field is immense. As we continue to push the boundaries of observational technology and theoretical models, we can expect to uncover even more about these enigmatic stellar giants. Their explosive deaths and the dramatic consequences of their mass loss are just one piece of the puzzle in understanding the evolution of the cosmos. Wolf-Rayet stars may seem like distant, otherworldly objects, but their impact on the universe is profound. Their study holds the key to unraveling some of the most fundamental mysteries of the universe, from the origins of heavy elements to the formation of black holes and the mechanics of supernova explosions. As we look to the future, the study of Wolf-Rayet stars will continue to play a central role in the field of astrophysics. New discoveries and advancements in technology will allow us to probe these stars in greater detail than ever before. We may even find that Wolf-Rayet stars are more common than we once thought, with many more of these cosmic giants waiting to be discovered in the far reaches of the universe. With each new revelation, we inch closer to understanding the life cycles of the most massive stars, the processes that drive their evolution, and the lasting legacy they leave behind. The story of Wolf-Rayet stars is one of extremes. These stars push the boundaries of what we know about stellar physics, revealing the incredible power and complexity of the universe. Their life cycles, marked by dramatic mass loss, explosive deaths, and the formation of exotic remnants, offer a glimpse into the workings of the cosmos at its most extreme. As we continue to study these stellar giants, we can expect to uncover even more about the nature of the universe and the forces that shape it. As we venture further into the enigmatic world of Wolf-Rayet stars, it's important to emphasize the role they play in enriching the universe with heavier elements. These stars, while remarkable for their size and power, are also fundamental to the chemical evolution of galaxies. The elements they produce, such as oxygen, carbon, and nitrogen, are the building blocks of life as we know it. Without Wolf-Rayet stars, and the supernovae or black holes they become, much of the universe's heavy elements would not exist. The material they release through their intense winds and explosive deaths is scattered across space, seeding the interstellar medium and enriching future generations of stars, planets, and even life itself. The aftermath of Wolf-Rayet stars' violent ends presents a complex picture of stellar remnants. As we mentioned earlier, some Wolf-Rayet stars undergo a dramatic collapse, eventually triggering a supernova explosion. These supernovae are some of the most energetic events in the universe, capable of briefly outshining an entire galaxy. The remnant left behind can be a neutron star, an object that is so dense that it contains the mass of several suns packed into a city-sized volume. In other cases, these stars collapse directly into a black hole, a region of space-time with such intense gravitational pull that not even light can escape it. The role of Wolf-Rayet stars in the creation of black holes is a particularly fascinating aspect of their life cycle. A black hole forms when a star's mass is so great that it overcomes all other forces, including the pressure exerted by nuclear fusion in the star's core, and collapses under its own gravity. This process is still an active area of research in astrophysics, and understanding it could lead to significant breakthroughs in our comprehension of the universe. The behavior of these collapsing stars, particularly in terms of how they shed mass and evolve in the final stages of their lives, remains one of the greatest puzzles in modern science. The collapse of a Wolf-Rayet star into a black hole is not a simple event. As the star approaches the end of its life, it may experience a series of unstable phases where its core contracts and heats up, causing powerful bursts of energy and radiation. These bursts, often detected as gamma-ray bursts, are thought to be associated with the formation of black holes. These high-energy explosions are among the most violent and dramatic events in the universe, and they can be observed from great distances. The origin of gamma-ray bursts is still debated, but many researchers believe that they are the result of Wolf-Rayet stars collapsing into black holes. The supernovae and black holes produced by Wolf-Rayet stars are not isolated events. They are part of the broader cycle of cosmic evolution, contributing to the recycling of matter in the universe. When a supernova occurs, the star's outer layers are blown off in a tremendous explosion, scattering elements such as iron and silicon across space. These elements are then incorporated into future generations of stars and planets. In the case of black holes, the intense gravity they exert can influence the surrounding space, pulling in gas and dust from nearby regions. This process, known as accretion, can lead to the formation of powerful jets of material that are ejected at nearly the speed of light. These jets can have a profound impact on their surrounding environment, influencing the formation of new stars and galaxies. As we examine the role of Wolf-Rayet stars in the cosmic cycle, it becomes clear that they are not just massive objects in the sky, they are essential players in the story of the universe. Without their intense radiation, powerful winds, and violent deaths, the universe would be a very different place. The elements that make up our world, the very building blocks of life, were forged in the hearts of these stars. The energy they release helps fuel the formation of new stars, planets, and galaxies, shaping the universe as we know it. Their deaths, in the form of supernovae and black holes, continue the cycle of creation and destruction that defines the universe. Moreover, the study of Wolf-Rayet stars has the potential to unlock new understanding of stellar evolution. While these stars are relatively rare, their properties make them key to understanding the processes that govern the birth and death of massive stars. By studying the chemical composition of these stars and their surrounding nebulae, scientists can learn about the conditions that existed in the early universe. The processes that lead to the formation of Wolf-Rayet stars are thought to be similar to those that occurred in the first generations of stars. By studying these stars, we can gain insights into the conditions that led to the formation of galaxies and the chemical enrichment of the universe. The detection and study of Wolf-Rayet stars in distant galaxies is also an exciting frontier in astronomy. By examining these stars and galaxies that are billions of light years away, scientists can learn about the conditions that existed in the early universe. This research could help us understand the role of massive stars in the formation of galaxies, and how they contribute to the cosmic recycling process. It may also shed light on the processes that led to the formation of the first black holes and the earliest supernovae. In addition to their role in the evolution of galaxies, Wolf-Rayet stars also provide valuable clues about the behavior of matter in extreme conditions. These stars exist in an environment where gravity, temperature, and radiation all work together in a delicate balance. The study of these stars and their surrounding nebulae can help scientists understand how matter behaves under extreme pressure and temperature. This knowledge could have far-reaching implications for a variety of fields, including nuclear physics, quantum mechanics, and even the study of black holes. The future of Wolf-Rayet star research is bright. With advancements in observational technology, such as the James Webb Space Telescope, astronomers will be able to study these stars in unprecedented detail. The ability to observe these stars in the infrared spectrum will provide new insights into their chemical composition, wind dynamics, and evolutionary paths. This, in turn, will help scientists build more accurate models of stellar evolution and the fate of massive stars. Furthermore, the study of Wolf-Rayet stars could have implications beyond the realm of astrophysics. Understanding the life cycle of these stars, their explosive deaths, and their contribution to the formation of heavy elements could offer insights into the processes that occur on other planets. For instance, it is possible that the elements produced by Wolf-Rayet stars were critical in the formation of the planets in our solar system, including Earth. If this is the case, then the study of these stars could help us understand the origins of life itself. As we look to the future, the study of Wolf-Rayet stars will continue to push the boundaries of what we know about the universe. These stars, with their incredible mass and energy, represent some of the most extreme and fascinating objects in the cosmos. Their dramatic mass loss, explosive deaths, and profound impact on the surrounding environment make them a key focus for astronomers and astrophysicists alike. Through continued observation and research, we can expect to unlock even more of the secrets these stars hold. The mysteries of Wolf-Rayet stars are far from being fully solved, and as we continue to explore their nature, we will undoubtedly gain new insights into the broader processes that govern the universe. Whether we are studying their winds, their chemical composition, or their final moments as supernovae or black holes, these stars are offering us a glimpse into the heart of the universe. Through these stars, we are not just learning about the life and death of massive objects, we are learning about the very building blocks of the universe itself. Wolf-Rayet stars stand as a testament to the sheer power and mystery embedded in the universe. These stars are not only the cosmic giants of their respective galaxies, but they also hold within them a critical key to understanding the entire life cycle of massive stars and the evolution of galaxies themselves. With each new discovery about their characteristics, behaviors, and the profound effects they have on their surroundings, scientists are peeling back layers of cosmic history that have remained hidden for billions of years. One of the most fascinating aspects of these stars is their intense winds. These winds, driven by radiation pressure, are among the most powerful in the universe. For a star like this, the radiation produced by nuclear fusion is so immense that it overpowers the force of gravity, pushing away the outer layers of the star at a staggering rate. This process, known as mass loss, plays a central role in the life cycle of Wolf-Rayet stars. The material that is lost in these winds is not merely scattered aimlessly into space. Rather, it becomes part of the interstellar medium, where it can eventually be incorporated into new stars, planets, and other celestial bodies. Through this process, Wolf-Rayet stars effectively recycle the elements in the universe, ensuring that the cosmic building blocks required for the formation of new stars and planetary systems are continually replenished. As we witness these colossal stars shedding their outer layers, we are also observing the early stages of the end of their existence. The loss of mass weakens the star's outer layers, creating an imbalance that leads to the eventual collapse of its core. This core, which has undergone many phases of nuclear fusion throughout the star's life, is composed mostly of heavier elements like carbon and oxygen. Once this core collapses, the result can be a spectacular explosion known as a supernova. Supernovae are incredibly energetic events, capable of briefly outshining an entire galaxy. These explosions are not only spectacular in terms of their sheer energy output, but they also serve as the final moments of a star's life, marking the end of one phase and the beginning of another. In the case of Wolf-Rayet stars, these explosions are especially significant because they occur in a way that leads to the creation of black holes. As the star's core collapses inward, it may eventually reach a point where nothing can stop it from collapsing further, not even the pressure exerted by nuclear fusion. This is when a black hole is formed. The connection between Wolf-Rayet stars and black holes is one of the most exciting frontiers in modern astrophysics. The formation of black holes is still a topic of intense research, and Wolf-Rayet stars provide a natural laboratory for studying the processes involved. The mass of a star plays a crucial role in determining whether it will become a black hole or a neutron star after its supernova explosion. Stars that are more massive than around 25 times the mass of the Sun are likely to collapse directly into black holes, while less massive stars may form neutron stars. The study of Wolf-Rayet stars can provide critical insights into this boundary, and help researchers understand the conditions that lead to the formation of black holes. Beyond their role in black hole formation, the violent deaths of Wolf-Rayet stars also have a profound impact on the surrounding space. When these stars explode in a supernova, the shockwave generated by the explosion travels through the interstellar medium, compressing gas and dust along the way. This process can trigger the formation of new stars, initiating a cycle of star birth and death that shapes the evolution of galaxies. In addition to creating new stars, supernovae enrich the surrounding space with heavier elements. These elements, produced through the fusion processes occurring in the star's core, are scattered across space when the star explodes, becoming part of the raw material for the next generation of stars and planets. While much has been learned about the final moments of Wolf-Rayet stars, there is still much that remains a mystery. One of the greatest questions that astronomers continue to investigate is how these stars evolved from their early, massive forms to the more stable, but still highly energetic, Wolf-Rayet phase. This transition is not fully understood, and the mechanisms that drive it are still being explored. For example, scientists are working to understand the role that rotation plays in the evolution of these stars. Some research suggests that the rapid rotation of a star may accelerate the process of mass loss, driving the star into the Wolf-Rayet phase much more quickly than it otherwise would. The detailed study of these stars, particularly their chemical composition and stellar winds, could provide the answers to these questions and more. Another key area of research involves the study of the surrounding nebulae that form around Wolf-Rayet stars. These nebulae, which are often composed of the same material that the star has shed through its winds, are a rich source of information about the star's history. By analyzing the chemical composition and structure of these nebulae, scientists can learn more about the processes occurring in the star's outer layers and gain insights into the mechanisms that drive its mass loss. This research is also important for understanding how the material shed by the star interacts with the surrounding environment. In some cases, these nebulae can form intricate and beautiful structures, such as the well-known WR nebulae, which are named after Wolf-Rayet stars. The continued study of Wolf-Rayet stars and their nebulae has important implications for our understanding of the broader universe. These stars are thought to be responsible for producing much of the heavy elements that are essential for life as we know it. The carbon, oxygen, and nitrogen that make up the world around us were likely forged in the cores of these massive stars. As these elements are dispersed into space through the explosion of a supernova, they contribute to the formation of new stars and planets. This process, known as nucleosynthesis, is a key part of the cosmic cycle that drives the evolution of galaxies, stars, and planets. By studying Wolf-Rayet stars, we gain a deeper understanding of the origin of the elements that make up the universe and the forces that shape its evolution. In addition to their role in the chemical enrichment of the universe, Wolf-Rayet stars also offer valuable clues about the early stages of galaxy formation. The stars we see today are the result of billions of years of cosmic evolution, during which galaxies have grown, merged, and evolved. The presence of Wolf-Rayet stars in distant galaxies allows us to glimpse the conditions that existed in the early universe, helping us understand how galaxies formed and how the first generation of stars came into being. By studying these stars and galaxies billions of light years away, astronomers can learn about the processes that led to the creation of galaxies and the first stars. The study of Wolf-Rayet stars is also a vital part of the ongoing search for extraterrestrial life. By understanding the life cycle of these stars, including the formation of heavy elements and the subsequent creation of new stars and planets, we are better equipped to explore the possibility that life exists elsewhere in the universe. If the elements necessary for life can be formed in the death throes of stars like Wolf-Rayet stars, it stands to reason that similar processes may have occurred elsewhere in the cosmos, potentially leading to the formation of planets that harbor life. Wolf-Rayet stars are some of the most fascinating and important objects in the universe. Their massive size, powerful winds, and explosive deaths play a crucial role in the evolution of galaxies, the formation of new stars and planets, and the creation of the heavy elements that are essential for life. As scientists continue to study these stars and their explosive ends, we can expect to uncover even more mysteries about the processes that shape the cosmos. Whether it's their role in the formation of black holes, the chemical enrichment of the universe, or their impact on the surrounding space, Wolf-Rayet stars are a key piece of the puzzle that is the universe. Their study not only helps us understand the death of massive stars but also sheds light on the origins of the elements that make up the very world we live in. As the study of Wolf-Rayet stars progresses, one of the most exciting aspects is the role they play in the greater cosmic narrative. These stars, despite their immense size and fiery temperament, are often short-lived. They burn through their fuel quickly and in spectacular fashion, making them rare and transient phenomena. The briefness of their lives, however, means that they can teach us an incredible amount about stellar evolution in a relatively short amount of time. To understand why Wolf-Rayet stars are so important, we must first look at their origins. These stars begin their lives as massive, blue giant stars, fusing hydrogen into helium in their cores. The initial stages of a massive star's life are marked by the process of nuclear fusion, which generates the immense energy that powers the star and allows it to shine. However, this fusion process is not sustainable for long in stars that are many times the mass of our Sun. As the star ages, it eventually begins to burn heavier elements in its core, moving from hydrogen to helium, and then to even heavier elements like carbon, neon, and oxygen. This process creates an unstable environment within the star, as the outer layers of the star are not in equilibrium with the core. The star's outer layers expand, and the radiation pressure from the core pushes against gravity, causing the outer layers to be ejected into space. The shedding of a star's outer layers is one of the defining characteristics of Wolf-Rayet stars. These stars expel a significant portion of their mass through intense stellar winds. The material that is ejected contains a high concentration of heavy elements like carbon and oxygen, which were created in the star's core through nuclear fusion. These elements are crucial for the formation of new stars, planets, and even life itself. In fact, some scientists theorize that the death of Wolf-Rayet stars and the subsequent explosion of supernovae play a central role in the creation of the elements necessary for life as we know it. Through these explosive deaths, Wolf-Rayet stars essentially seed the universe with the building blocks for the next generation of stars and planetary systems. As we examine the fate of these stars, one thing becomes clear: Wolf-Rayet stars are on a collision course with death, and their end comes in one of the most dramatic and explosive ways possible. After shedding their outer layers, the remaining core of the star collapses inward. If the core is sufficiently massive, it will continue collapsing until it forms a black hole. If the core is somewhat less massive, it may collapse into a neutron star, another exotic object with intense gravity and density. However, regardless of whether a black hole or neutron star forms, the death of the Wolf-Rayet star is marked by the violent and cataclysmic explosion known as a supernova. The supernova explosion that follows the death of a Wolf-Rayet star is a truly awe-inspiring event. The energy released in a supernova is so immense that it can briefly outshine an entire galaxy, and the shockwave created by the explosion sends out a burst of radiation that can be detected across vast distances in the universe. These supernovae also play an essential role in the universe's chemical evolution. The elements produced during the fusion process inside the star's core are released into the surrounding space during the explosion, enriching the interstellar medium with heavy elements. This material is then incorporated into future generations of stars and planetary systems, continuing the cycle of stellar birth and death that drives the evolution of galaxies. While supernovae are incredibly powerful events, the aftermath of these explosions can be even more fascinating. The collapse of a Wolf-Rayet star's core can result in the formation of a black hole, one of the most mysterious and enigmatic objects in the universe. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape. The formation of black holes from the collapse of massive stars is one of the key pieces of evidence supporting the theory of general relativity, and the study of these objects continues to provide valuable insights into the nature of space and time itself. In the case of Wolf-Rayet stars, the connection between these massive stars and black holes is not just a theoretical concept but an observable phenomenon. The process by which these stars shed their outer layers and collapse into black holes has been studied extensively, and astronomers have even observed the formation of black holes from the remnants of massive stars in real time. The study of these events helps scientists refine their understanding of how black holes are formed and what happens in the moments leading up to their creation. The more we learn about the deaths of Wolf-Rayet stars, the closer we come to understanding the nature of black holes and the fundamental forces that govern the universe. Another critical aspect of Wolf-Rayet stars is their role in shaping the structure of galaxies. The powerful winds and radiation emitted by these stars influence the interstellar medium around them, affecting the formation and evolution of other stars. In some cases, the intense radiation from a Wolf-Rayet star can trigger the formation of new stars, leading to a process known as starburst. Starbursts occur when a region of space experiences an unusually high rate of star formation, often as a result of the intense energy and radiation produced by a nearby Wolf-Rayet star. These bursts of star formation play a key role in the growth and evolution of galaxies, helping to build the cosmic structures that we see today. Additionally, the study of Wolf-Rayet stars also sheds light on the conditions present in the early universe. These stars are thought to be a relic of a time when the universe was still young and its first generations of stars were forming. The discovery of Wolf-Rayet stars in distant galaxies allows astronomers to probe the conditions of the early universe and gain insights into the processes that led to the formation of the first stars and galaxies. Understanding how Wolf-Rayet stars evolve and die provides valuable information about the cosmic environment in which they formed and offers clues about the conditions that existed in the earliest stages of cosmic history. Wolf-Rayet stars are among the most fascinating and important objects in the universe. Their massive size, powerful winds, and dramatic deaths offer a unique glimpse into the life cycle of stars and the evolution of galaxies. From their birth as blue giants to their violent end as supernovae or black holes, these stars are at the center of some of the most exciting and mysterious phenomena in astrophysics. Their study not only helps us understand the fate of massive stars but also provides key insights into the chemical evolution of the universe, the formation of black holes, and the conditions that existed in the early universe. As we continue to study these incredible stars, we will undoubtedly uncover even more mysteries about the forces that shape the cosmos and the intricate dance of creation and destruction that defines the universe. Wolf-Rayet stars are, without a doubt, one of the most captivating phenomena in the universe, offering astronomers a unique window into the extreme ends of stellar evolution. Their importance goes far beyond their fiery and short-lived nature, as they also provide vital insights into the formation of new stars, the creation of heavy elements, and the ultimate fate of massive stars. In understanding their complexities, we can better appreciate the processes that shape galaxies and the cosmic structure at large. One of the key reasons these stars are so interesting is the way in which their extreme luminosity and mass interact with the surrounding environment. The powerful stellar winds that Wolf-Rayet stars generate strip away vast amounts of their mass, creating huge nebulae made of gas and dust. These nebulae, known as Wolf-Rayet nebulae, are often observed in the vicinity of these stars and are an essential feature of their life cycle. The radiation and the fast-moving particles emitted from these stars cause significant changes in the interstellar medium, heating up the surrounding gas and affecting the rate at which new stars are born. The process is, in a sense, a cosmic feedback loop. While the energy and winds of Wolf-Rayet stars can potentially trigger the formation of new stars, their death also disperses the elements needed for the next generation of stellar birth. This dynamic has profound implications for the study of stellar populations and galaxies. By observing how Wolf-Rayet stars influence their surroundings, astronomers can gather important information about the star formation rates and the characteristics of the interstellar medium in galaxies. Their ability to impact the galaxy's star-forming regions makes them key to understanding the evolutionary cycles of galaxies. It also explains why Wolf-Rayet stars are often found in regions of intense star formation or near areas where starbursts are happening. Their intense radiation can compress nearby clouds of gas, sparking the birth of new stars, even as the Wolf-Rayet star itself is nearing the end of its life. Another aspect of Wolf-Rayet stars that draws interest is their extreme temperatures. These stars can have surface temperatures upwards of 50,000 Kelvin, far hotter than our Sun, which sits at a temperature of around 5,500 degrees Celsius. This intense heat is a result of the star's rapid fusion process, which leads to the production of heavy elements in its core. These high temperatures also cause the star to emit massive amounts of ultraviolet radiation, a significant factor in their role in the cosmos. This ultraviolet radiation not only shapes the chemical composition of the surrounding gas but also plays a part in the heating of intergalactic space. Moreover, Wolf-Rayet stars are thought to be crucial players in the creation of some of the heaviest elements in the universe, including gold and uranium. These elements are produced during the late stages of stellar evolution, particularly in supernovae. When a Wolf-Rayet star explodes in a supernova, it releases an extraordinary burst of energy and heavy elements into space. This process, known as nucleosynthesis, forms the building blocks of the next generation of stars and planets. Some of the heavier elements formed during these explosions may even be incorporated into the formation of new planetary systems, potentially contributing to the creation of life-supporting elements on planets in other parts of the universe. In addition to their contribution to the formation of elements, the study of Wolf-Rayet stars is also key to understanding the phenomena that drive black hole formation. These stars are one of the main progenitors of black holes, providing one of the most direct pathways to the formation of these enigmatic cosmic objects. As mentioned earlier, when the core of a Wolf-Rayet star collapses after shedding its outer layers, it may form a black hole. The study of this process is essential in understanding the behavior of matter under extreme conditions and gives insight into the fundamental nature of spacetime itself. Astronomers have been able to observe some of these processes firsthand, thanks to advances in space telescopes and other observational techniques. For instance, the Hubble Space Telescope has captured stunning images of Wolf-Rayet stars and their associated nebulae. These images not only provide a visual representation of the chaotic and violent nature of these stars but also allow scientists to study the composition and structure of the stellar winds and the surrounding gas. In addition to Hubble, the upcoming James Webb Space Telescope is expected to provide even more detailed observations of Wolf-Rayet stars, offering new opportunities to explore these stellar giants in unprecedented detail. As researchers continue to examine the depths of these stars, they also focus on the different ways in which Wolf-Rayet stars can vary in their final stages. Not all Wolf-Rayet stars die in the same manner. The mass of the star, the rate at which it sheds material, and the particular conditions of the surrounding environment all play a role in determining the outcome. Some Wolf-Rayet stars explode as supernovae, creating an intense burst of light and energy. Others may collapse directly into black holes without an accompanying supernova explosion, leaving behind a region of space where no light escapes, a black hole. This difference in outcomes is part of the complexity that makes the study of Wolf-Rayet stars so intriguing, as it highlights the delicate balance of forces at play in the final moments of a star's life. Wolf-Rayet stars also raise fundamental questions about the life cycles of stars in the early universe. These massive stars were likely much more common in the early stages of cosmic history, when the universe was still young and populated by the first generations of stars. Understanding how these stars lived and died in the past could offer important insights into the formation of galaxies and the evolution of the universe as a whole. The study of Wolf-Rayet stars, particularly those in distant galaxies, can provide a glimpse into this early period of cosmic history, allowing scientists to reconstruct the conditions that led to the formation of the galaxies we see today. In addition, Wolf-Rayet stars can tell us a great deal about the dynamics of supernovae. While the explosion of these stars is one of the most well-known and dramatic events in astrophysics, it is also one of the least understood. Supernovae are difficult to study because they are inherently unpredictable and often occur in distant galaxies, making it challenging to observe them in real time. However, by studying the properties of Wolf-Rayet stars and their associated nebulae, scientists can begin to unravel the mystery of how supernovae occur and what role they play in the evolution of galaxies. Understanding the mechanisms behind these explosions could help to answer some of the most profound questions in astrophysics, including the nature of dark energy, the fate of the universe, and the behavior of matter in extreme conditions. Ultimately, Wolf-Rayet stars serve as a cosmic laboratory, offering a wealth of information about the life cycles of stars, the formation of heavy elements, and the behavior of black holes. Their study continues to push the boundaries of our understanding of the universe and provides valuable clues about the fundamental processes that govern the cosmos. Whether they are emitting powerful stellar winds, enriching the interstellar medium with heavy elements, or collapsing into black holes, Wolf-Rayet stars are at the center of some of the most exciting and mysterious phenomena in astrophysics. As our ability to observe these stars improves, so too does our understanding of the intricate mechanisms that shape the universe. With each new discovery, we are one step closer to unlocking the secrets of these stellar giants and uncovering the mysteries of the cosmos. As we continue to explore the fascinating world of Wolf-Rayet stars, it's important to delve deeper into their role within the larger framework of stellar evolution. These stars provide a crucial glimpse into the intense, short-lived processes that govern the fate of the universe's most massive stars. Their behavior is governed by a delicate interplay of gravitational forces, fusion, and the way they lose mass over time, which ultimately determines their ultimate fate. One of the most intriguing aspects of Wolf-Rayet stars is their ability to shed such massive amounts of mass during their lifetimes. The stellar winds of these stars are unlike anything seen in smaller stars. They blow at speeds up to 3,000 km per second, and they can expel anywhere from 10 to 30 times the mass of the Sun over the course of a few million years. These winds are driven by the immense radiation pressure exerted by the star's hot, luminous surface. As the star's core fuses elements into heavier ones, the energy released forces the outer layers of the star to expand and be expelled into space. Over time, this continuous loss of mass leads to the reduction of the star's overall size and ultimately its transformation into a more compact remnant. The high temperatures of Wolf-Rayet stars, often over 50,000 Kelvin, are the result of the complex fusion processes occurring in their cores. These stars burn through their fuel much faster than smaller stars like our Sun, and their massive size causes them to burn hotter and brighter. The core of a Wolf-Rayet star is primarily composed of heavier elements, including carbon and oxygen. These elements are formed in the earlier stages of the star's life as it fuses hydrogen into helium in the core. As the star ages, it begins to burn helium into heavier elements, eventually leading to the formation of elements like iron and nickel. This process is known as nucleosynthesis and plays a crucial role in the creation of the heavy elements that make up the universe. This intense fusion process, however, is not without consequences. As the star exhausts its fuel, the balance between the inward pull of gravity and the outward push from radiation becomes unstable. In a typical star, when the core runs out of fuel, it will collapse and cause a supernova explosion. However, Wolf-Rayet stars, with their extreme masses, follow a slightly different path. Their supernovae are among the most energetic in the universe, capable of expelling massive amounts of energy and elements into the surrounding space. These explosions not only release incredible amounts of radiation and energy, but they also trigger the formation of new elements, enriching the interstellar medium and contributing to the creation of new stars, planets, and possibly even life. As the star nears the end of its life, its outer layers are progressively blown away by the intense radiation pressure from the core. This outer envelope is what gives Wolf-Rayet stars their characteristic appearance. Unlike other stars, which have a more uniform outer layer of gas, the outer layers of Wolf-Rayet stars are thin and translucent, with much of the mass having been lost in the form of stellar wind. The stripped core of a Wolf-Rayet star becomes increasingly unstable, and it is this core that is eventually left behind after the outer layers are shed. This remnant is often composed primarily of helium or carbon, depending on the mass of the star, and can eventually collapse into a neutron star or, in the case of the most massive Wolf-Rayet stars, a black hole. What makes these final stages so extraordinary is the level of complexity involved. The transition from a massive star to a black hole is not a simple process, and there are many factors that influence the eventual outcome. For example, the mass of the star is a critical determinant of whether it will end as a neutron star or a black hole. A Wolf-Rayet star that is particularly massive will undergo a dramatic collapse into a singularity, where gravity becomes so intense that not even light can escape. On the other hand, slightly less massive stars may not have enough mass to form a black hole and may instead collapse into a neutron star, an incredibly dense object that can still emit radiation. Neutron stars and black holes are both fascinating objects in their own right. Neutron stars, for instance, are incredibly compact, with densities so high that a teaspoon of neutron star material would weigh as much as the entire human population. These stars also possess intense magnetic fields and can emit beams of radiation in the form of pulsars. Black holes, on the other hand, are often considered one of the greatest mysteries in astrophysics. Their immense gravity distorts spacetime itself, creating a point where not even light can escape. The event horizon, the boundary beyond which nothing can escape, is a defining feature of black holes, and studying them can provide valuable insights into the nature of gravity, spacetime, and the fundamental structure of the universe. What's fascinating is that Wolf-Rayet stars are often the precursor to these exotic objects. By studying these stars in detail, scientists can better understand the processes that lead to the formation of black holes and neutron stars. These stellar giants offer an opportunity to study the extreme conditions that arise during the collapse of a massive star, giving astronomers a glimpse into the final moments of stellar death. Observations of Wolf-Rayet stars can help scientists pinpoint the characteristics of the material surrounding these objects, how they interact with their surroundings, and what happens during the transition from star to black hole or neutron star. However, the mystery surrounding these stars doesn't end there. There are still many questions left unanswered. For example, the exact mechanisms behind the formation of black holes from Wolf-Rayet stars are still not fully understood. Some models predict that massive stars should undergo a violent supernova explosion that expels much of the star's outer material before collapsing into a black hole, while others suggest that some Wolf-Rayet stars might collapse directly into a black hole without a supernova explosion at all. This variation in outcomes challenges our understanding of the processes that govern stellar evolution, and it highlights how much more there is to learn. Another area of interest is the role of Wolf-Rayet stars in the broader context of galaxy formation. These stars, with their intense radiation and powerful winds, contribute to the chemical enrichment of galaxies. As they explode in supernovae or collapse into black holes, they release vast amounts of heavy elements into the surrounding interstellar medium. This enrichment has far-reaching consequences, as it provides the raw materials for the formation of new stars and planetary systems. Without these explosions, the heavy elements necessary for the formation of rocky planets and life as we know it might not exist. Moreover, Wolf-Rayet stars are also key players in the ongoing study of the early universe. These stars were likely much more common in the early stages of cosmic history when the universe was still young. They are thought to have played a significant role in the formation of the first galaxies and the evolution of the universe's chemical composition. By studying the properties of these stars and distant galaxies, scientists can reconstruct the conditions that led to the formation of galaxies, stars, and even life. The study of Wolf-Rayet stars offers a window into the past, allowing us to trace the origins of the universe and the mechanisms that have shaped it over billions of years. The excitement surrounding Wolf-Rayet stars is not just about what we have learned, but also about what we have yet to discover. As telescopes and observational techniques continue to improve, we can expect to uncover even more mysteries about these enigmatic stellar giants. From their complex evolution and role in the creation of heavy elements to their final transformation into black holes or neutron stars, Wolf-Rayet stars remain one of the most fascinating and elusive phenomena in the universe. Each new discovery brings us closer to understanding the intricate processes that govern the lives and deaths of the most massive stars in existence. In the grand scheme of the universe, Wolf-Rayet stars are but a brief flash of brilliance, burning bright and fast before ultimately fading away. Yet, in that brief lifespan, they offer a wealth of knowledge that shapes our understanding of the cosmos. As we continue to explore these extraordinary objects, we move one step closer to unraveling the mysteries of the universe and understanding the fundamental forces that govern all matter and energy. Through the study of Wolf-Rayet stars, we gain not only a deeper understanding of the stars themselves but also the vast, interconnected web of processes that shape the universe as a whole. As we continue our exploration of Wolf-Rayet stars, we delve deeper into their enigmatic nature and how their evolution can reveal so much about the fundamental workings of the universe. There's something almost mystical about these massive, fleeting stars, whose existence embodies the extremes of stellar life. The explosive transformations that occur as these stars reach the end of their lives offer a critical link between the birth of elements in the cosmos and the formation of celestial bodies, like black holes, that challenge our understanding of physics. Understanding Wolf-Rayet stars is crucial because they represent the final stages of the most massive stars before they either become supernovae or collapse into black holes. This is where the lines between conventional stellar evolution and some of the universe's most extreme phenomena blur. When you look at these stars, you're looking at the birth of new worlds, the creation of heavy elements, and the ultimate fate of the largest stars in the universe. Now, let's talk about the astrophysical processes at play in a Wolf-Rayet star. At the heart of these massive giants, nuclear fusion is in full swing, with the star fusing helium into heavier elements like carbon, oxygen, and eventually iron. This process causes the star to burn through its fuel at an incredibly rapid pace, much faster than smaller stars like our Sun. The extreme temperature and pressure inside the core of the Wolf-Rayet star create conditions for these heavy elements to form, but as they get heavier, they are also less stable. When iron begins to form, nuclear fusion stalls because iron fusion consumes energy rather than releasing it. This is where things get interesting because the buildup of iron in the core signals the beginning of the end for a Wolf-Rayet star. As iron accumulates, it doesn't generate the pressure needed to resist the force of gravity, and the star begins to collapse. In an ordinary star, this collapse would result in the creation of a white dwarf, a neutron star, or a black hole. In the case of the most massive stars, those that started as Wolf-Rayet stars, the collapse leads to a supernova explosion. The supernova, in essence, is the universe's way of recycling heavy elements. The enormous explosion blasts the outer layers of the star into space, creating a shockwave that spreads outwards, enriching the interstellar medium with elements like iron, carbon, oxygen, and more. These elements will eventually form new stars, planets, and even life. The energy released in the explosion is so intense that it can outshine an entire galaxy for a brief period. This catastrophic end marks the transition of the Wolf-Rayet star into its final form, depending on its mass. For some, the remaining core will continue to collapse under its own gravity, leading to the formation of a neutron star or a black hole. Neutron stars, as dense as the cores of atomic nuclei, are incredibly compact objects that exhibit extreme properties. The most massive neutron stars can have magnetic fields trillions of times stronger than Earth's and are capable of emitting beams of radiation like a cosmic lighthouse. On the other hand, the most massive Wolf-Rayet stars collapse directly into black holes, where the matter becomes so dense that the gravitational pull becomes so strong that nothing, not even light, can escape. These black holes are not just a scientific curiosity. They are key to understanding the nature of space and time itself. Black holes distort the very fabric of space-time, creating phenomena like time dilation and gravitational lensing, which astronomers use to probe the depths of the universe. The transition from a Wolf-Rayet star to one of these exotic remnants offers crucial insights into the fundamental forces at play in the universe. It also sheds light on one of the most fascinating and mysterious processes in astrophysics: how stars die and how their deaths shape the universe. Understanding the specific pathways that lead from Wolf-Rayet stars to black holes or neutron stars will help astronomers refine their models of stellar evolution, providing a clearer picture of the life cycles of the universe's most massive stars. The study of these stellar giants also reveals something important about the fundamental question of why certain stars go supernova, and others form black holes. What is the threshold that determines the path a massive star will take? These are questions that astrophysicists are still grappling with. The exact mass threshold for when a star will collapse into a black hole, for example, is still not completely understood. The evolution of Wolf-Rayet stars challenges our assumptions about this threshold, as some models predict that a star can collapse directly into a black hole without a supernova at all. Interestingly, these massive stars also offer important clues about the earliest moments of the universe. In the early stages of the cosmos, massive stars were far more common, and they were responsible for much of the element production in the universe. The collapse of these stars into black holes or neutron stars played a role in seeding the universe with the heavy elements that are essential for the formation of planets, including Earth, and life itself. By studying the remnants of these stars, scientists are able to trace the evolution of galaxies, stars, and elements throughout cosmic history. The role of Wolf-Rayet stars in galaxy formation is another exciting avenue of research. These stars, with their explosive ends and powerful winds, influence the evolution of galaxies in profound ways. As they release massive amounts of energy and heavy elements, they help shape the environments in which new stars and planets form. In fact, some of the most active regions of star formation in galaxies are regions that contain Wolf-Rayet stars. By studying these regions, astronomers can better understand how galaxies evolve over time and how the most massive stars contribute to that evolution. The study of Wolf-Rayet stars is also crucial for understanding the formation of exotic objects like black holes and neutron stars. While these objects are relatively well studied, the exact mechanisms that lead to their formation are still not entirely clear. For example, the process of a Wolf-Rayet star collapsing into a black hole involves a complex interplay of mass, radiation, and gravity, and there is still much to learn about the details of this process. Some theories suggest that the presence of certain types of matter in the star's outer layers could affect the outcome of the collapse, possibly leading to the formation of a black hole without a supernova explosion. In the grander context of cosmic evolution, Wolf-Rayet stars represent the final chapter in the lives of the universe's most massive and luminous stars. Their transformation into supernovae, neutron stars, or black holes marks the culmination of a process that began with the formation of the star billions of years ago. By studying these stars, we can gain insights not only into the fate of individual stars but also into the broader processes that shape the universe, including the formation of galaxies, black holes, and even the elements that make up everything we know. Moreover, the mystery surrounding these stars doesn't stop at their final stages. One particularly intriguing question is what happens to the material expelled by Wolf-Rayet stars after their death. The heavy elements released during supernova explosions have a profound effect on the universe, influencing everything from the formation of new stars to the creation of planets and the development of life. The dust and gas expelled by these massive stars are a key ingredient in the process of stellar evolution, and understanding how this material interacts with the surrounding environment is crucial for understanding how galaxies evolve. As we continue to study these stellar giants, new technologies and advancements in observational astronomy will undoubtedly unlock even more secrets about Wolf-Rayet stars and their role in the universe. High-resolution telescopes and space-based observatories will allow scientists to study these stars in greater detail, potentially discovering new features of their behavior and interactions. With each new discovery, we get one step closer to understanding the fundamental nature of the cosmos and the life cycles of the universe's most extreme stars. The story of Wolf-Rayet stars is far from over. As we venture deeper into understanding these cosmic giants, we recognize that the work done today will shape our knowledge for generations to come. Modern telescopes like the Hubble Space Telescope, the James Webb Space Telescope, and the very next generation of space observatories, with their ability to capture unprecedented details of faraway stars, will provide us with new data and reveal fresh mysteries. As technology advances, we'll begin to glimpse more of these stars in all their glory and unravel their more complex behaviors, including how their surrounding environments are affected by the immense power they exert. One of the most tantalizing aspects of Wolf-Rayet stars is the sheer magnitude of the energy they release. We've spoken about their end stages, but what about the dramatic processes occurring as they evolve? Wolf-Rayet stars are marked by fierce winds, stellar winds that are far stronger than the solar wind we experience here on Earth. These winds blow off the outer layers of the star, stripping it of its mass at an extraordinary rate. In fact, the mass loss in Wolf-Rayet stars can be up to 10 million times stronger than that of our Sun. Over time, this intense mass loss causes these stars to shrink significantly, which only accelerates their eventual collapse. These winds also contribute to the formation of nebulae, the colorful clouds of gas and dust seen in some of the most beautiful images of space. The Wolf-Rayet star's wind contributes to the chemical enrichment of the galaxy, seeding it with elements that will go on to form new stars, planets, and potentially even life. Another key area of research is the relationship between Wolf-Rayet stars and the regions in which they are found. These stars tend to appear in star-forming regions, often in nebulae or clusters, where gas and dust abound. This is because Wolf-Rayet stars themselves are born from the most massive clouds of gas, which collapse under their own gravity to form new stars. These regions are teeming with new star formation, and the massive energy from Wolf-Rayet stars can play a significant role in the evolution of the entire star-forming region. The intense radiation and stellar winds can trigger the formation of new stars, further influencing the dynamics of the region and potentially even setting the stage for further stellar evolution. But even with all that we know about these massive stars, there's still a great deal we don't understand. Take, for example, the role of Wolf-Rayet stars in the cosmic cycle of matter. When these stars explode as supernovae, they eject vast amounts of material, especially heavy elements like iron, oxygen, and carbon, into the surrounding interstellar medium. This process contributes to the ongoing formation of new stars, as these elements act as the building blocks for future stellar systems. This recycling of material is essential for the continuous evolution of galaxies. Some models even suggest that the material expelled by supernovae could eventually lead to the formation of new stars, planets, and even life as we know it. The study of Wolf-Rayet stars thus becomes a key piece in the puzzle of understanding the cosmic cycle of matter. What makes these stars particularly fascinating is the mystery surrounding their initial formation. To put it simply, how do such enormous stars form in the first place? The exact mechanism by which massive stars like Wolf-Rayet stars come into existence remains a subject of intense debate. Some theories suggest that these stars form in dense clusters, where they can rapidly accumulate mass. Others propose that massive stars may form in isolation, collecting gas and dust from their surroundings. Understanding this process is crucial because it could shed light on the formation of galaxies and even the early stages of the universe. Wolf-Rayet stars are not just interesting in terms of their death. Their birth and evolution are equally fascinating. Their rapid evolution from young, massive stars to their eventual collapse is a complex journey that raises many questions about the interplay of physical forces like gravity, radiation pressure, and stellar winds. In some sense, studying the lives of these stars provides us with a window into the nature of the most extreme astrophysical environments in the universe. As we consider the broader implications of these stars, one cannot help but think about their ultimate role in the formation of galaxies. The death of a Wolf-Rayet star doesn't just mark the end of a stellar life, but it plays a crucial role in shaping the surrounding environment. The shockwaves from supernovae can trigger the formation of new stars, and the heavy elements released during the explosion become the building blocks for future generations of stars and planets. Wolf-Rayet stars are, in a very real sense, responsible for the ongoing evolution of galaxies. They help fuel the cycle of star birth and death that drives the universe's expansion, ultimately contributing to the ongoing creation of the cosmic tapestry we observe today. Yet, despite our current understanding of Wolf-Rayet stars, many questions remain. For example, we are still uncertain about the precise factors that determine whether a massive star will end its life as a black hole or a neutron star. In the case of Wolf-Rayet stars, the answer is not straightforward. Some models suggest that the mass of the star plays a critical role in determining its final fate, while others point to factors such as the amount of mass lost through stellar winds or the chemical composition of the star. These uncertainties provide a compelling reason for continued research into the life cycles of massive stars. In addition to the questions surrounding their death, we also have a host of unanswered questions regarding their formation. What triggers the creation of such massive stars in the first place? How do they gather the immense amounts of gas and dust necessary for their formation? Are there other, unknown mechanisms at play that we have yet to discover? These are the kinds of questions that keep astrophysicists up at night, as the answers could change our entire understanding of stellar evolution and even the nature of the universe itself. As we look ahead to the future, the study of Wolf-Rayet stars will undoubtedly continue to evolve. New telescopes, advanced simulations, and increasingly sophisticated models will help answer some of the most pressing questions about these enigmatic stars. But even as we learn more about Wolf-Rayet stars, new mysteries will likely emerge, keeping us on the edge of our seats as we explore the vast and mysterious cosmos. Whether through the study of their powerful winds, their complex role in galaxy formation, or the exact processes by which they collapse into black holes or supernovae, there is still so much to learn. The story of Wolf-Rayet stars is a testament to the complexity and beauty of the universe. These massive stars, with their stunning power and dramatic ends, offer us a glimpse into the extreme conditions that govern the cosmos. Their lives, marked by rapid evolution and violent death, are a reflection of the constant change that characterizes the universe as a whole. As we continue to study these stellar giants, we gain a deeper understanding of the forces that shape the cosmos and our place within it. And in doing so, we unlock the mysteries of some of the universe's most awe-inspiring phenomena. As we continue our journey into the heart of Wolf-Rayet stars, it's important to emphasize the significance of these stars in our quest to understand the universe. They serve as natural laboratories for studying the behavior of matter under extreme conditions. These stars are not only a crucial part of the cosmic ecosystem, but they also help us to understand more fundamental aspects of astrophysics, from the nature of stellar formation to the ultimate fate of stars. One of the most striking characteristics of Wolf-Rayet stars is their short-lived nature. Despite their enormous mass and power, these stars don't burn for long compared to less massive stars like our Sun. A typical Wolf-Rayet star may only last a few million years, far shorter than a Sun-like star, which can live for billions of years. This brief lifespan is a result of the immense pressure and temperature within the star, which causes it to burn through its nuclear fuel at an accelerated rate. The high luminosity and energy output of Wolf-Rayet stars also contribute to their relatively short lifespans. Despite their youth, these stars burn brightly and quickly, leaving behind a stunning, yet fleeting legacy in the universe. This rapid evolution leads to one of the most interesting aspects of Wolf-Rayet stars: their profound influence on their surrounding environment. The intense radiation and strong stellar winds from these stars can shape the interstellar medium, the vast expanse of gas and dust that exists between stars and a galaxy. As Wolf-Rayet stars shed their outer layers, they enrich the surrounding gas clouds with heavy elements such as carbon, oxygen, and nitrogen. These elements, which are essential for life as we know it, play a key role in the creation of new stars and planets. In a sense, Wolf-Rayet stars are the cosmic architects, sculpting the very building blocks of future star systems. Their effects on the environment don't stop there. The powerful stellar winds from Wolf-Rayet stars can also trigger shockwaves in nearby regions of space, compressing gas clouds and potentially triggering the formation of new stars. This process is known as triggered star formation, and it's one of the ways in which these stars influence their surroundings. In regions where large numbers of Wolf-Rayet stars are present, their collective energy can lead to the creation of massive stellar nurseries, where new stars are born in the wake of the older generation's death throes. But it's not just the surrounding gas clouds that are affected by Wolf-Rayet stars. These stars also influence the larger galactic structure. Their powerful winds and explosive deaths shape the overall dynamics of their host galaxies. As these stars eject their outer layers in violent outbursts, they can create large, expanding bubbles of gas, which can disrupt the existing galactic structure. In some cases, these bubbles can even lead to the formation of galactic outflows, where gas is expelled from the galaxy altogether. These outflows, which can stretch across vast distances, can have significant implications for the evolution of galaxies, influencing star formation rates and the distribution of matter throughout the galaxy. The interplay between Wolf-Rayet stars and their environment is a dynamic and complex process, one that has profound implications for the formation and evolution of galaxies. The energy and material that these stars release contribute to the ongoing cycle of birth, death, and rebirth in the universe. As we continue to study Wolf-Rayet stars and their effects on their surroundings, we gain a deeper understanding of the forces that drive the evolution of galaxies and the cosmos as a whole. As we move from the environmental impact of these stars to their internal processes, we must delve deeper into the physics that governs their behavior. The core of a Wolf-Rayet star is a furnace of extreme heat and pressure. Within this core, hydrogen is fused into helium through nuclear fusion, releasing vast amounts of energy in the process. But as the star ages, it begins to run out of hydrogen fuel, and its core contracts under the force of gravity. This contraction causes the core to heat up, and it begins fusing heavier elements like helium, carbon, and oxygen. Each stage of fusion produces an increasingly complex series of reactions, with each new element requiring higher temperatures and pressures to fuse. This process of fusion creates the layers of the star, with the lighter elements being fused in the outer layers and the heavier elements forming in the core. The energy produced by nuclear fusion in the core creates an outward pressure that counteracts the force of gravity, preventing the star from collapsing in on itself. However, as the star's mass increases, the pressure from the core becomes so intense that it overwhelms the outward pressure from fusion. This imbalance causes the star to collapse, leading to a chain reaction that ultimately results in the star's death. The specifics of this process vary depending on the mass of the star. In the case of Wolf-Rayet stars, which are among the most massive stars in the universe, this process is especially extreme. These stars burn through their nuclear fuel at an accelerated rate, and their core reaches incredibly high temperatures and pressures. As the star approaches the end of its life, it sheds its outer layers through intense stellar winds, revealing the dense, hot core at the center. This core, known as a stellar remnant, is the heart of the star that survives its death. The fate of this remnant depends on the mass of the star. If the star is massive enough, the core will collapse further, eventually forming a black hole. If the core is slightly less massive, it may form a neutron star, a dense object composed almost entirely of neutrons. In either case, the remnant represents the final stage of the star's evolution, a testament to the intense forces at work within these massive stars. The formation of a black hole or neutron star is a dramatic and violent event. It represents the culmination of a long and complex process of stellar evolution. But the story of a Wolf-Rayet star does not end with its death. The explosion that follows, whether it's a supernova or the formation of a black hole, has far-reaching consequences. These events are among the most powerful phenomena in the universe, releasing immense amounts of energy and ejecting large amounts of material into space. This material can go on to form new stars, planets, and even life. Wolf-Rayet stars are more than just massive, short-lived cosmic giants. They are the engine of galactic evolution, the catalysts for the formation of new stars, and the creators of the elements that make life possible. Through their death and explosive transformation, they contribute to the ongoing cycle of creation and destruction that shapes the universe. Their study reveals not only the complexities of stellar evolution but also the fundamental processes that drive the growth and evolution of galaxies. Wolf-Rayet stars serve as a reminder of the vast and intricate forces at play in the cosmos, forces that we are only beginning to understand. And as we continue to study these enigmatic stars, we uncover new layers of the universe's mysteries, taking us one step closer to unraveling the secrets of the cosmos itself. The aftermath of a Wolf-Rayet star's collapse is where the true spectacle lies. The star's eventual death leaves behind an enormous void in space, often marked by a brilliant supernova explosion. When a Wolf-Rayet star undergoes a supernova, it releases an extraordinary amount of energy, enough to briefly outshine an entire galaxy. The star's outer layers are expelled into space, enriching the interstellar medium with a wide array of elements. This process not only marks the end of the star's life but also plays a critical role in the creation of new stellar systems and even planetary systems. The material ejected from the explosion can mix with surrounding gas clouds, contributing to the birth of new stars, planets, and potentially the ingredients for life itself. But what exactly happens when a Wolf-Rayet star explodes? The mechanism of such an event is complex and requires a deep dive into the physics of stellar explosions. In the case of massive stars like Wolf-Rayets, the process begins when the core of the star becomes unstable. The core, which has already gone through several stages of nuclear fusion, collapses under its own gravity. The outer layers, no longer supported by the pressure from the core, are ejected outward in a violent explosion. This explosion is what we observe as a supernova. The shockwave from the explosion can cause intense radiation to be emitted, along with a variety of elements such as iron, nickel, and heavier elements like gold and platinum. This process of stellar death is critical for the cosmic cycle. When these elements are spread across the galaxy, they become part of the raw materials for future generations of stars. The death of Wolf-Rayet stars is integral to the creation of the very building blocks for life as we know it. The elements released into space during their demise provide the raw materials for planets, asteroids, and even life forms. In essence, these stars are the cosmic recyclers, constantly creating the elements that will fuel the next generation of stars and planets. After the explosion, what remains of the Wolf-Rayet star is either a neutron star or a black hole, depending on the mass of the core. If the core's mass is below a certain threshold, it becomes a neutron star, an incredibly dense remnant where matter is packed so tightly that electrons and protons combine to form neutrons. Neutron stars are incredibly small, often only about the size of a city, but they contain the mass of several suns. These remnants are magnetic and rotate rapidly, emitting intense beams of radiation. If the core is sufficiently massive, however, the collapse will continue, leading to the formation of a black hole. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. The core's collapse into a singularity marks the final stage of the star's life cycle, and the surrounding material is consumed by the black hole, further growing its mass. Despite their mysterious and somewhat ominous nature, black holes are crucial to our understanding of space-time and the limits of physical law. The creation of a black hole or neutron star is not the end of the story, however. The immense gravity of these remnants can have far-reaching consequences for their surroundings. For example, a black hole's gravitational pull is so strong that it can distort spacetime, bending the path of light and even slowing down time itself near its event horizon. In some cases, the powerful gravitational forces from a black hole can disrupt nearby stars, pulling them into its embrace and consuming them in a process called tidal disruption. But these extreme remnants of dead stars do more than just warp space-time. They also help shape the galaxies in which they reside. In some cases, black holes, particularly supermassive ones, are believed to be at the center of galaxies, influencing the entire galactic structure. The forces at play in these regions are so intense that they can affect the orbits of stars and even influence star formation rates. A black hole's gravitational influence extends far beyond its immediate vicinity, making it a key player in the ongoing evolution of galaxies. As we step back and consider the broader implications of Wolf-Rayet stars and their eventual collapse, we start to see a larger picture emerge. These stars play an essential role in the cosmic recycling process, taking the heavy elements created in their cores and scattering them across the universe. This process of stellar death and rebirth is vital for the ongoing formation of new stars and planets. The elements released during a supernova or black hole formation can serve as the building blocks for future generations of stars, planets, and even life itself. Moreover, Wolf-Rayet stars serve as a critical part of the cosmic life cycle. They provide a glimpse into the most extreme processes that govern the universe, from the immense gravitational forces at work within a black hole to the violent shockwaves emitted by a supernova. Understanding how these stars function and how they die helps us to better understand the larger mechanisms that drive the universe itself. Whether we're examining the birth of a star, the collapse of a massive star, or the formation of a black hole, these phenomena offer valuable insights into the workings of the cosmos. Wolf-Rayet stars are not just cosmic oddities. They are the engine that drives much of the evolution of galaxies and the interstellar medium. Their explosive deaths seed the universe with the heavy elements necessary for life, and their extreme physics helps scientists probe the limits of our understanding of space and time. While they may be short-lived in the grand scheme of the universe, their impact is immense and far-reaching, affecting the very fabric of the cosmos. The study of these stars is just beginning to reveal the depth of their importance. As technology advances, scientists are able to gather more data, allowing us to understand these enigmatic objects with greater precision. With telescopes capable of observing distant stars and advanced simulations modeling the physics of these objects, we are slowly piecing together the story of Wolf-Rayet stars. These stars are one of the many cosmic mysteries that continue to captivate scientists and astronomers around the world. The Wolf-Rayet star is a reminder of the ever-changing and dynamic nature of the universe. It embodies the constant cycle of creation, destruction, and rebirth that characterizes the cosmos. From the intense radiation and winds that sculpt their surroundings to their explosive deaths that shape the future of galaxies, these stars are more than just fleeting giants in the sky. They are integral players in the grand cosmic narrative. As we continue to study them, we unlock new insights into the universe's past, present, and future, taking one step closer to unraveling the many mysteries of space. As we continue to delve deeper into the complexities of Wolf-Rayet stars, it's important to recognize that their significance extends far beyond the mere spectacle of their death throes. Their role in the cosmic ecosystem is vital, as they act as powerful engines for enriching the universe with essential elements. The materials released during their explosive finales serve as the building blocks for future generations of stars, planets, and even life itself. These stellar giants are responsible for generating many of the heavier elements, such as gold, platinum, and uranium, which are crucial for the formation of planets, as well as the existence of life. Without the catastrophic deaths of these stars, the universe would be a very different place. But their importance doesn't end with their explosive demise. The study of Wolf-Rayet stars also helps to illuminate many other aspects of stellar evolution and the dynamic processes at work in the universe. These stars are often in close proximity to other massive stars, and the interaction between them can lead to fascinating phenomena. For example, some Wolf-Rayet stars are part of binary star systems, where their intense radiation and powerful stellar winds can strip material from their companion stars. This interaction can lead to the creation of even more exotic objects, such as X-ray binaries, where one of the stars is a black hole or neutron star, and material from its companion is funneled into an accretion disk, emitting X-rays as it is heated to extreme temperatures. Another fascinating aspect of Wolf-Rayet stars is their connection to the larger evolution of galaxies. These massive stars are often found in star-forming regions known as nebulae, which are clouds of gas and dust where new stars are born. Wolf-Rayet stars, with their immense luminosity and strong stellar winds, can profoundly impact the surrounding gas clouds. They can clear out large regions of the nebula, allowing for the formation of new stars and altering the overall structure of the galaxy. In some cases, the intense radiation from a Wolf-Rayet star can trigger the collapse of nearby gas clouds, leading to the formation of new stars. In this way, these stars play an active role in shaping the future of their host galaxies. Wolf-Rayet stars are also an important part of the broader understanding of stellar evolution. They are thought to be a late stage in the life cycle of massive stars, and studying them provides crucial insights into the processes that govern the life and death of stars. In many ways, they represent the final chapter in the story of a massive star's existence, offering a glimpse into the complex physics that governs stellar life cycles. By studying these stars, scientists are able to test theoretical models of stellar evolution and improve our understanding of the forces at play in the most extreme environments of the universe. One of the key features that sets Wolf-Rayet stars apart from other stars is their extremely high mass. These stars are often several times more massive than the Sun, and their intense radiation and powerful stellar winds can strip away large amounts of material from their outer layers. This process, known as mass loss, is a defining characteristic of Wolf-Rayet stars. In some cases, the mass loss is so extreme that the star sheds almost all of its outer layers, leaving behind only a dense, hot core. This core is composed primarily of carbon and oxygen, the remnants of nuclear fusion processes that have taken place in the star's interior. As the star approaches the end of its life, it undergoes a series of dramatic changes. The fusion of heavier elements in the core leads to the creation of elements like silicon and iron, which, when they accumulate in large enough quantities, cause the core to collapse under the force of gravity. This collapse triggers the star's final explosion, the supernova. The outer layers of the star are ejected into space, while the core becomes a neutron star or black hole, depending on its mass. The extreme conditions found in the remnants of Wolf-Rayet stars are a fascinating area of study for astrophysicists. Neutron stars, for example, are some of the densest objects in the universe, with a mass several times that of the Sun packed into a sphere no larger than a city. The physics of these objects is still not fully understood, and studying them can provide valuable insights into the nature of matter under extreme conditions. Likewise, black holes, particularly those formed from the collapse of massive stars like Wolf-Rayet stars, are some of the most mysterious and enigmatic objects in the universe. The study of black holes challenges our understanding of physics, particularly in areas such as general relativity and quantum mechanics. But perhaps one of the most fascinating aspects of studying Wolf-Rayet stars is their role in the cosmic evolution of galaxies. As we mentioned earlier, these stars are often found in star-forming regions, where their powerful winds and radiation can influence the formation of new stars. The energy they release can also affect the larger environment of the galaxy, triggering the formation of new structures such as nebulae, star clusters, and even entire galaxies. Wolf-Rayet stars, in this sense, are not just passive objects, they actively shape the evolution of the universe, leaving a lasting imprint on the cosmic landscape. Their role in the chemical enrichment of the universe is also critical. The elements created during the collapse of Wolf-Rayet stars are scattered throughout the galaxy, eventually becoming part of the raw material for new stars, planets, and even life. Without the contribution of these massive stars, the universe would be vastly lacking in the essential elements needed for the formation of planets like Earth, and life as we know it might never have arisen. In this way, the death of a single Wolf-Rayet star can have far-reaching implications, impacting the future of the entire galaxy and the potential for life in the universe. So, the next time you look up at the night sky, consider the Wolf-Rayet stars and their fascinating life cycles. These stellar giants, though short-lived in the grand scheme of things, play an essential role in shaping the universe. Their explosive deaths, often visible as brilliant supernovae, seed the galaxy with the elements that will go on to form new stars and planets. Their extreme environments challenge our understanding of physics and help us to probe the limits of our knowledge about the universe. And in their final moments, they leave behind remnants that continue to influence the cosmic landscape long after they have vanished from view. In the grand cosmic cycle, the death of a Wolf-Rayet star is not an end, but rather a beginning. The energy, material, and insights gained from studying these stars provide a glimpse into the ever-evolving nature of the universe. They are a testament to the dynamic and ever-changing forces that govern the cosmos, and they continue to fascinate astronomers, physicists, and stargazers alike. As we continue to explore the mysteries of the universe, the study of Wolf-Rayet stars will undoubtedly remain a crucial piece of the puzzle in our quest to understand the forces that shape the very fabric of existence. As we continue exploring the captivating world of Wolf-Rayet stars, we begin to appreciate the many layers of complexity that define these stellar behemoths. They represent an essential part of the cosmic life cycle, bridging the gap between the birth of stars and their eventual death. But beyond their role in the life cycle of stars, they also serve as a key to understanding some of the most extreme conditions in the universe. One of the most intriguing aspects of Wolf-Rayet stars is the composition of their outer layers. These stars are classified into two main types, WN stars, which primarily consist of nitrogen-rich material, and WC stars, which are characterized by carbon-rich outer layers. The composition of these stars offers a rare opportunity for astronomers to study the intricate processes that occur within a star's core and its outer envelope. As we mentioned earlier, Wolf-Rayet stars are in the later stages of stellar evolution, and the intense fusion processes taking place within their cores lead to the formation of increasingly heavier elements. This includes elements like carbon, oxygen, and nitrogen, essential building blocks of life. When these elements are released into the interstellar medium, they contribute to the chemical enrichment of the galaxy, laying the foundation for future generations of stars and planets. The surface temperatures of Wolf-Rayet stars are another fascinating aspect of their nature. These stars can reach temperatures exceeding 100,000 Kelvin, far hotter than the Sun, which has a surface temperature of about 5,500 Kelvin. This intense heat is responsible for the strong stellar winds that blow off the outer layers of the star. These winds are so powerful that they can strip away much of the star's mass, leaving behind a dense, hot core. The mass loss is so extreme that, in some cases, the star can lose up to 50% of its initial mass during its lifetime. The result is a star that is much smaller and more compact than it was in its earlier stages, but much more luminous, radiating vast amounts of energy into space. These massive outflows of material are not without consequence. The winds from Wolf-Rayet stars can interact with the surrounding interstellar medium, creating large nebulae and shock waves that propagate through space. These interactions can lead to the formation of complex structures such as H2 regions, where hydrogen gas is ionized by the intense ultraviolet radiation from the star. The dynamics of these interactions are still being studied, as they provide valuable insight into the processes that govern the birth, evolution, and death of stars, as well as the formation of galaxies. The fate of a Wolf-Rayet star is determined by its mass. Stars that are between 25 and 40 times the mass of the Sun are thought to end their lives as Wolf-Rayet stars before they explode in a supernova. The explosion is triggered when the core collapses under the force of gravity, releasing an enormous amount of energy that can briefly outshine an entire galaxy. This explosion, known as a Type II supernova, is one of the most violent events in the universe, releasing vast amounts of energy and scattering elements like carbon, oxygen, and iron across space. These elements are crucial for the formation of planets, and their dispersion into the interstellar medium enriches the surrounding gas clouds, contributing to the formation of new stars and planetary systems. However, not all Wolf-Rayet stars end their lives in a supernova. In some cases, the core of the star may be massive enough to collapse into a black hole. Black holes are some of the most enigmatic and fascinating objects in the universe, with gravity so intense that not even light can escape from them. The process by which a Wolf-Rayet star collapses into a black hole is still not fully understood, but it is thought to be closely related to the star's mass, rotation, and the way in which it loses mass through stellar winds. A star that loses enough of its outer layers may not have enough mass left to trigger a supernova, and instead, its core may collapse directly into a black hole. This is a key area of study for astrophysicists, as it challenges our understanding of the final stages of stellar evolution. Even after the star has reached the end of its life, the remnants of a Wolf-Rayet star can continue to influence the surrounding region for millions of years. The supernova explosion or the formation of a black hole can send shock waves through the surrounding gas, triggering the collapse of nearby gas clouds and leading to the formation of new stars. In this way, the death of a Wolf-Rayet star is not an isolated event but part of a larger process of star formation and galactic evolution. The remnants of these stars are often found in star-forming regions, where their energy and material continue to shape the future of the galaxy. These regions of star formation are some of the most active and dynamic areas in the universe. They are often characterized by dense clouds of gas and dust, where new stars are being born. Wolf-Rayet stars play an important role in these regions, as their intense radiation and stellar winds can trigger the collapse of nearby gas clouds, leading to the birth of new stars. This process, known as triggered star formation, is an essential part of the life cycle of galaxies. By studying the interactions between Wolf-Rayet stars and their surrounding environment, astronomers can learn more about the complex processes that govern the formation of stars and galaxies. The study of Wolf-Rayet stars also provides valuable insights into the larger-scale structure of the universe. These stars are often found in regions of the galaxy known as star clusters, where they are surrounded by other massive stars. These clusters are some of the oldest and most massive objects in the universe, and they provide a unique window into the early history of the galaxy. By studying the properties of these star clusters and the role of Wolf-Rayet stars within them, astronomers can gain a better understanding of the processes that led to the formation of galaxies and the evolution of the universe as a whole. Another fascinating aspect of Wolf-Rayet stars is their potential to help us better understand the nature of dark matter and dark energy. These mysterious substances make up the majority of the universe's mass-energy content, yet they remain elusive and poorly understood. The study of Wolf-Rayet stars and their behavior in different environments could provide clues to the properties of dark matter and dark energy, particularly in how they influence the dynamics of galaxies and the large-scale structure of the universe. While we may not yet have a complete understanding of these cosmic mysteries, the study of Wolf-Rayet stars offers a promising avenue for future research and discovery. Wolf-Rayet stars are among the most intriguing and enigmatic objects in the universe. Their massive size, extreme luminosity, and dramatic life cycle make them a fascinating subject of study for astronomers and astrophysicists alike. These stars are not only important for understanding the life and death of stars but also for shedding light on the larger processes that shape the universe, from the formation of galaxies to the creation of elements that are essential for life. Whether they explode in a supernova or collapse into a black hole, Wolf-Rayet stars leave a lasting imprint on the cosmos, continuing to influence the universe long after they have reached the end of their lives. As we continue to study these stars, we will undoubtedly unlock even more secrets of the universe, deepening our understanding of the forces that govern the cosmos and our place within it. As we continue delving deeper into the mysterious lives of Wolf-Rayet stars, we must explore not just their physical attributes and final fates, but also their profound impact on the surrounding environments and on our understanding of the cosmos. These stellar giants do more than just shine brightly in the sky. They are agents of change, transforming their environments, shaping the structure of galaxies, and influencing the course of cosmic evolution. One of the most remarkable features of Wolf-Rayet stars is the effect their intense radiation and stellar winds have on the gas and dust surrounding them. The powerful winds blowing from these stars are much faster and denser than those of less massive stars. These winds can reach speeds of up to 3,000 kilometers per second, more than 10 times faster than the wind blowing from our Sun. This immense force is responsible for blowing away the outer layers of the star, and sometimes even its entire outer envelope, exposing the hot, dense core at the center. The material expelled by these stars contributes significantly to the interstellar medium, the vast expanse of gas and dust that fills the spaces between stars and a galaxy. Wolf-Rayet stars are a key source of heavy elements, including carbon, oxygen, nitrogen, and various other metals, that are expelled into space during their final stages. These elements are critical in the formation of new stars, planets, and even life itself. The process of stellar winds carrying away the outer layers of Wolf-Rayet stars, a phenomenon known as mass loss, is a crucial part of the stellar life cycle. It helps to seed the universe with these heavy elements, enriching the interstellar medium and setting the stage for the creation of future generations of stars. But it is not just the stellar winds that are responsible for these cosmic changes. The immense energy released by these stars, through both their radiation and their stellar winds, can create shock waves that travel through the surrounding gas. These shock waves are not just a byproduct of the star's existence. They play a critical role in shaping the gas clouds around the star. When these shock waves interact with the gas, they can compress it to the point where new stars are born. This process, known as triggered star formation, is one of the most important mechanisms driving the creation of new stars in the universe. Wolf-Rayet stars also contribute to the creation of nebulae, vast clouds of gas and dust that are often illuminated by the intense radiation from the star itself. These nebulae are not only beautiful but also serve as some of the most productive regions of the universe, where new stars and planetary systems are constantly forming. The most famous example of a nebula influenced by a Wolf-Rayet star is the nebula surrounding the Wolf-Rayet star WR104, located in the constellation Sagittarius. This nebula, known as the Pinwheel Nebula, is a stunning example of how Wolf-Rayet stars can shape the interstellar medium and create complex, beautiful structures. Beyond their role in star formation, Wolf-Rayet stars also play an essential part in the evolution of galaxies. These stars are often found in the centers of star-forming regions, and their powerful radiation and winds can trigger the collapse of nearby gas clouds, initiating the formation of new stars. This process is a vital part of the cosmic cycle, as it ensures that galaxies continue to form new stars, even as older stars die off. The birth and death of stars are inextricably linked, and the role of Wolf-Rayet stars in this cycle cannot be overstated. The final stages of a Wolf-Rayet star's life are a time of extreme instability. These stars are characterized by their rapid rotation, and as they lose mass through their stellar winds, they often become more compact and more rapidly spinning. This increase in rotational speed can have significant effects on the star's evolution, potentially leading to the formation of strange and unusual objects, such as gamma-ray bursts, GRBs. GRBs are incredibly powerful explosions that can release as much energy in a few seconds as the Sun will emit in its entire lifetime. These explosions are thought to be linked to the collapse of massive stars, including Wolf-Rayet stars, and are believed to be one of the most extreme events in the universe. There is still much that remains unknown about the final stages of a Wolf-Rayet star's life, particularly in terms of how it transforms into either a supernova or a black hole. Much of this uncertainty stems from the complex and poorly understood processes that govern the behavior of such massive stars. One of the key factors that influences the fate of a Wolf-Rayet star is its mass. As we mentioned earlier, stars that are between 25 and 40 times the mass of the Sun are thought to undergo a supernova explosion, while more massive stars might collapse directly into black holes. However, the exact mechanism by which a Wolf-Rayet star undergoes this transformation is still a subject of intense research. Some theories suggest that the presence of a strong magnetic field in the star's core could influence the way in which the star collapses, leading to the formation of a black hole. Others propose that the star's rapid rotation might play a critical role, allowing the star to shed its outer layers before the core collapses into a black hole. Regardless of the specifics, what remains clear is that the death of a Wolf-Rayet star is an event of extraordinary significance, capable of creating some of the most extreme phenomena in the universe. In the aftermath of the death of a Wolf-Rayet star, the surrounding region is often left in a state of chaos. Supernova explosions can trigger the formation of new stars, while the collapse of the star into a black hole can lead to the creation of a powerful accretion disk, a swirling mass of gas and dust that surrounds the black hole. This disk can emit intense radiation as the material is pulled toward the black hole, and in some cases, it can produce powerful jets of matter that shoot out from the black hole's poles. These jets are among the most powerful and energetic phenomena in the universe, and they serve as another reminder of the extreme forces at play in the lives of Wolf-Rayet stars. One of the key challenges in studying Wolf-Rayet stars is their rarity. These stars are relatively short-lived compared to other types of stars, lasting only a few million years before they explode or collapse. This short lifespan makes them difficult to observe, especially since they are often located in distant parts of the galaxy. However, advances in astronomical technology and the development of new observational techniques have made it increasingly possible to study these stars in greater detail. Telescopes like the Hubble Space Telescope and the Very Large Telescope in Chile have provided astronomers with unprecedented views of Wolf-Rayet stars and their environments, allowing for more accurate measurements and deeper insights into their behavior. Additionally, new simulations and models are being developed to predict the behavior of these stars and their eventual fate. These models take into account factors like stellar mass, rotation, and mass loss, and they provide valuable predictions about the final moments of a Wolf-Rayet star's life. As we continue to gather more data, it is likely that we will gain a deeper understanding of these incredible stars and their role in the cosmic cycle of birth, life, and death. The study of Wolf-Rayet stars also has implications for our understanding of the universe as a whole. These stars serve as natural laboratories for testing the laws of physics under extreme conditions, and by studying them, we can learn more about the forces that govern the evolution of stars and galaxies. Wolf-Rayet stars are also crucial for understanding the chemical evolution of the universe, as they are responsible for producing and dispersing heavy elements like carbon, oxygen, and nitrogen, key ingredients for life as we know it. Wolf-Rayet stars are not only among the most fascinating and enigmatic objects in the universe, but they also serve as a vital link in the chain of cosmic events that shape the universe. From their massive size and extreme luminosity to their role in the formation of new stars and galaxies, these stars provide a unique window into the workings of the universe. Their life cycles, marked by intense radiation, stellar winds, and dramatic deaths, leave an indelible mark on the cosmos. As we continue to study these stars, we can expect to uncover even more secrets about the nature of the universe and our place within it. As we continue to explore the lives and legacies of Wolf-Rayet stars, it's essential to take a closer look at their fascinating interaction with other cosmic phenomena. Their sheer mass, intense radiation, and powerful winds make them influential players in the larger-scale events that unfold in galaxies. For example, when a Wolf-Rayet star goes supernova or collapses into a black hole, the surrounding environment is transformed dramatically. But the implications of these events extend far beyond the star itself, influencing the structure of entire galaxies and affecting the lives of countless other stars. The process of stellar death, particularly in the case of a Wolf-Rayet star, isn't just about one star disappearing. It's part of a broader mechanism that drives galactic evolution. One of the key ways this happens is through the process known as feedback. In essence, the energy released by these massive stars in the form of radiation and stellar winds can have a profound effect on the gas and dust in the surrounding region. This can compress nearby clouds of gas, triggering the formation of new stars. This process is known as triggered star formation. What's particularly fascinating is that this feedback loop helps regulate the balance between star formation and the dispersal of gas in galaxies. Without the influence of stars like Wolf-Rayets, galaxies would not be able to sustain a constant cycle of star birth, stellar evolution, and star death. These stars also play a pivotal role in shaping the future of the star clusters they inhabit. Wolf-Rayet stars are often found in groups called stellar clusters that contain other massive stars. As these stars evolve, their intense energy and stellar winds impact one another. They can strip away each other's outer layers, influencing the formation of new stars, and in some cases, creating complex systems of stars and planets that would not have otherwise formed. These stellar clusters, filled with Wolf-Rayet stars, become nurseries for future generations of stars and planets. Without these clusters, the process of galactic and star formation would look vastly different. Another fascinating aspect of Wolf-Rayet stars is their role in generating the most powerful explosions in the universe, supernovae. The exact mechanism by which a Wolf-Rayet star explodes is still an area of active research, but what is known is that these massive explosions are among the most violent events that can occur in the universe. When a Wolf-Rayet star runs out of nuclear fuel, it can no longer sustain the pressure needed to counterbalance its gravity. The core of the star collapses under its own weight, triggering a massive release of energy. This is the supernova explosion. The force of this explosion can outshine an entire galaxy, releasing as much energy in a single burst as the star would emit over its entire lifetime. In many cases, this explosion is so intense that it can briefly outshine the rest of the stars in its galaxy. The shockwave generated by the explosion can propagate through the surrounding gas and dust, triggering the formation of new stars and reshaping the interstellar medium. Supernovae are critical in the ongoing evolution of galaxies because they help to recycle the material that forms new stars. The heavy elements produced in the explosion, such as iron and gold, are scattered into space, where they mix with the surrounding gas and dust. Over time, these elements become part of the next generation of stars, planets, and even life. The aftermath of a supernova can leave behind the remnants of the original Wolf-Rayet star, which are sometimes found in the form of neutron stars or black holes. Neutron stars, formed from the collapse of a star's core, are incredibly dense objects with a mass greater than that of the Sun packed into a sphere only about the size of a city. These stars can rotate at incredibly high speeds, generating intense magnetic fields that can affect the surrounding environment. In some cases, neutron stars can even interact with each other, creating phenomena like gravitational waves, which are ripples in spacetime that travel outward from the source of the disturbance. These waves are one of the most exciting areas of research in modern astrophysics, and provide a unique way of studying the most extreme objects in the universe. In some cases, however, the collapse of a Wolf-Rayet star leads directly to the formation of a black hole. Unlike neutron stars, black holes are objects where gravity is so intense that not even light can escape. The creation of a black hole marks the final, catastrophic end of a star's life, and while these objects are invisible to the naked eye, their presence can be detected by the effect they have on nearby matter. When a black hole forms, it pulls the material from the surrounding gas, forming an accretion disk, a swirling mass of gas and dust that is heated to incredibly high temperatures as it spirals inward. This disk emits intense radiation, which can outshine the star itself, creating some of the most powerful light sources in the universe. The matter surrounding the black hole is not just a passive bystander, however. In some cases, black holes can launch high-speed jets of matter and radiation from their poles. These jets, which can extend for thousands of light years, are one of the most fascinating features of black holes. They are thought to be powered by the black hole's intense gravitational field, which pulls in surrounding material and accelerates it to nearly the speed of light. The jets produced by these black holes are not only incredibly energetic but also serve as a beacon for astronomers to study. By observing the radiation emitted by the jets, scientists can learn about the behavior of black holes and the processes that occur in the extreme environments surrounding them. As we look further into the future of Wolf-Rayet stars, we find that their influence will continue to be felt for billions of years. The supernovae and black holes they leave behind will continue to shape the galaxies they inhabit, providing the building blocks for future generations of stars, planets, and galaxies. The elements produced by these stars are essential for life as we know it, as they are the building blocks of everything from the water in our oceans to the DNA in our cells. In many ways, we are all made of the same stuff as these distant stars, and the death of a Wolf-Rayet star is a crucial step in the process of life in the universe. The study of Wolf-Rayet stars offers a unique glimpse into the final stages of stellar evolution and provides valuable insights into the forces that shape the universe. These stars may be short-lived, but their impact on the cosmos is profound. As we continue to study them, we gain a better understanding of the forces that govern the universe, the processes that shape galaxies, and the fundamental nature of the stars that light up the night sky. The mysteries of Wolf-Rayet stars may take many more years to fully unravel, but with each discovery, we move one step closer to understanding the very heart of the universe itself. Wolf-Rayet stars are not only fascinating in their own right, but they are also crucial to the ongoing evolution of the universe. From their intense stellar winds and radiation to their ultimate fate as supernovae or black holes, these stars are responsible for some of the most extreme and beautiful phenomena in the cosmos. Their life cycles contribute to the creation of new stars, the distribution of heavy elements, and the shaping of galaxies. As we continue to study them, we not only learn more about the stars themselves but also gain valuable insights into the broader processes that govern the cosmos. Wolf-Rayet stars may be rare, but their influence is anything but small. They are, quite simply, among the most powerful and fascinating objects in the universe. Wolf-Rayet stars, with their extraordinary life cycles, not only captivate the curiosity of astronomers, but also play an essential role in our understanding of the universe's evolution. The key to their importance lies in their sheer size, brightness, and the way they expel vast quantities of matter into space. Their ability to influence their surroundings is so profound that the repercussions of their existence ripple across the cosmos in ways that go far beyond the star itself. These stars, in their final stages, are like cosmic powerhouses, generating the heavy elements that ultimately form planets, and even life itself. As previously mentioned, one of the defining characteristics of a Wolf-Rayet star is its intense stellar wind. This wind, which is composed of particles and gases being ejected from the surface of the star at high speeds, is a direct result of the star's extreme temperature and luminosity. These winds can reach speeds of several thousand kilometers per second, and over time, they strip away the outer layers of the star. This process leads to the star losing a substantial fraction of its mass. It's not just a side effect of the star's age, it's the very mechanism that determines how the star will die and what legacy it will leave behind. For instance, As the outer layers are blown away by the winds, a Wolf-Rayet star becomes exposed to the full force of its internal processes. What remains is a core composed largely of heavier elements like carbon and oxygen. This core is far more compact and dense than the outer layers of the star. As the star continues to evolve, it becomes more and more unstable. The internal pressures build up, and eventually, they overcome the gravitational forces trying to hold the star together, resulting in a violent explosion known as a supernova. However, not all Wolf-Rayet stars meet the same fate. Some, particularly the most massive ones, may not explode in a supernova at all. Instead, their collapse may lead directly to the formation of a black hole. The distinction between a supernova and a black hole is a subtle yet incredibly important one. While both represent the final stage in the life of a massive star, a supernova results in the release of massive amounts of energy and material into space, whereas a black hole forms when the collapsing star's mass is so great that not even light can escape its gravitational pull. The formation of a black hole marks the ultimate point of no return, and once a black hole forms, it begins to influence its surroundings in ways that we are only beginning to understand. When a Wolf-Rayet star explodes as a supernova, the event is so powerful that it often outshines an entire galaxy for a brief period of time. These supernovae are not just spectacular fireworks in the sky, they are the birthplaces of new elements. The fusion processes occurring in the dying star's core create a variety of heavier elements, many of which are necessary for life to exist. Elements like iron, nickel, and gold are produced in the star's final moments, and are then dispersed into space by the shockwave of the explosion. These elements become part of the gas and dust clouds that will later form new stars, planets, and other celestial bodies. Without these supernovae, the elements necessary for life as we know it would never have been created. In a way, the death of a Wolf-Rayet star is also the birth of something new. The heavy elements produced in the supernova enrich the interstellar medium, providing the building blocks for future generations of stars. These new stars, which will form from the clouds of gas and dust enriched by the death of the Wolf-Rayet star, will have the same potential for greatness. Some will be born massive and luminous, while others will take on smaller, more stable forms. Each new generation of stars brings with it the possibility of new planetary systems, new forms of life, and new cosmic mysteries to explore. Wolf-Rayet stars and their explosive deaths also have a significant impact on the surrounding environment. When they expel material into space, the surrounding gas and dust are altered, both chemically and physically. The shockwave from a supernova can trigger the formation of new stars by compressing nearby gas clouds. This is known as triggered star formation. As the material from the explosion collides with and compresses these clouds, the pressure and density increase, potentially leading to the collapse of the gas and the birth of new stars. This process is vital for the ongoing creation of stars and galaxies, and it illustrates the interconnectedness of the universe. The interaction between a Wolf-Rayet star and its environment is further complicated by the presence of nearby objects. If the star is part of a binary system, where two stars orbit each other, the winds from one star can influence the evolution of its companion. In some cases, the interaction between the two stars can lead to the exchange of mass, with one star siphoning off material from the other. This process, known as mass transfer, can cause one of the stars to evolve faster, potentially leading to its collapse into a black hole or supernova. These interactions can result in the formation of exotic objects like X-ray binaries, where a compact object such as a black hole or neutron star is accompanied by a regular star, or even the creation of gravitational wave events, which have become a significant focus of modern astrophysical research. Furthermore, Wolf-Rayet stars are thought to be the progenitors of some of the most energetic phenomena observed in the universe. One of these phenomena is gamma-ray bursts, GRBs, which are brief but extremely powerful bursts of gamma-ray radiation. These bursts are thought to be caused by the collapse of massive stars into black holes or neutron stars. GRBs are some of the most energetic explosions in the universe, and their study has provided astronomers with new insights into the fundamental processes that drive the death of massive stars. Some of the most distant and energetic objects we observe, such as distant galaxies and quasars, may owe their creation to these powerful bursts. As we look to the future, the study of Wolf-Rayet stars will continue to play a crucial role in our understanding of the universe. With advancements in technology and observation techniques, we will be able to observe these stars in greater detail than ever before. The launch of new space telescopes, such as the James Webb Space Telescope, will allow scientists to peer deeper into the cosmos and uncover the mysteries of these stars. As we gain a better understanding of Wolf-Rayet stars, we will learn more about the processes that drive the evolution of galaxies, the formation of black holes, and the origins of the elements that make up the universe. In many ways, the study of these stars is a reminder of the interconnectedness of all things in the universe. The death of a single Wolf-Rayet star can have far-reaching consequences, shaping the future of galaxies and the very elements that make life possible. As we continue to explore the cosmos and unravel its mysteries, we may find that these enigmatic stars are just one piece of a much larger puzzle, one that continues to unfold in ways that we can only begin to comprehend. Wolf-Rayet stars may be rare, but their influence on the universe is anything but small. Their explosive deaths, the elements they produce, and the cosmic structures they help shape make them essential to the ongoing evolution of the cosmos. These stars are a testament to the complexity and beauty of the universe, and their study will undoubtedly continue to inspire astronomers for generations to come. As we delve deeper into the nature of Wolf-Rayet stars, their significance grows even clearer. Not only do these cosmic giants shape the stellar populations around them, but they also give us vital clues about the origins of some of the most intriguing phenomena we observe today. Their unique characteristics make them a key focal point in the study of stellar evolution, supernova mechanisms, and the larger processes of cosmic recycling. One of the most fascinating aspects of Wolf-Rayet stars is their role in the synthesis of heavy elements. The core of a Wolf-Rayet star is a furnace of nuclear reactions, where lighter elements like hydrogen and helium are fused into heavier ones, including carbon, oxygen, and nitrogen. This process, known as nucleosynthesis, takes place under extreme temperatures and pressures. As the star continues to burn its fuel, it creates an even wider variety of elements, including the heavier metals like iron and nickel. When a Wolf-Rayet star reaches the end of its life and explodes in a supernova, the heavy elements produced during this process are released into the surrounding space. These elements are then incorporated into new generations of stars and planets. This is a critical aspect of stellar life cycles because it explains how the elements essential for life, including carbon, oxygen, and nitrogen, came to be present in the universe. The creation and distribution of these elements are what makes life possible on planets like Earth. Without the violent deaths of stars like the Wolf-Rayet, the elements we depend on would not be here. In fact, it's believed that the metals and elements produced by stars like Wolf-Rayet stars have been instrumental in shaping the chemistry of galaxies. These elements contribute to the formation of new stars, planets, and even the complex molecules that form life. Without these heavy elements, the universe would be a very different place. Understanding the specifics of how these elements are created and spread through space offers essential insights into both the past and future of our own galaxy, as well as others. But the story doesn't end with the creation of elements. The explosive deaths of Wolf-Rayet stars also have dramatic effects on the surrounding interstellar medium, which is the diffuse matter that exists between stars. The shockwaves from these explosions heat the surrounding gas, causing it to ionize, which can lead to the formation of nebulae, vast clouds of gas and dust. These nebulae are not only beautiful to look at through telescopes, but they are also nurseries for new stars. In this way, Wolf-Rayet stars are not just the end of one cycle, but the beginning of another. The process of supernova explosions also helps to seed galaxies with the material needed to form new star systems. The shockwave from a supernova has the power to compress gas clouds, which can then collapse under their own gravity to form new stars. This is how star formation proceeds in the wake of a Wolf-Rayet star's death. This phenomenon of star formation triggered by supernovae is essential to the creation of new stars and galaxies. It also leads to the creation of planets and other celestial objects, further driving the ongoing evolution of the universe. In addition to their role in stellar and planetary formation, Wolf-Rayet stars are also linked to some of the most energetic and mysterious phenomena in the universe. One of the most intriguing phenomena associated with the death of these massive stars is the formation of gamma-ray bursts, GRBs. These bursts of high-energy gamma radiation are thought to be the result of the collapse of massive stars, including Wolf-Rayet stars, into black holes. GRBs are among the most powerful events in the universe, and they release as much energy in a few seconds as the Sun will release over its entire lifetime. The study of GRBs has provided astronomers with crucial insights into the behavior of the most extreme objects in the universe. By studying the afterglows of GRBs, scientists have been able to learn more about the environments around these dying stars and the conditions under which these explosive events take place. These discoveries have deepened our understanding of the life cycles of massive stars and the role they play in shaping the larger cosmic landscape. Furthermore, the connection between Wolf-Rayet stars and black holes is another area of intense interest for astronomers. When a massive star reaches the end of its life, it has the potential to collapse directly into a black hole without undergoing a supernova explosion. This process is known as direct collapse. The black hole that forms from this collapse can then go on to influence its surroundings in profound ways. For instance, the powerful gravitational field of a black hole can distort the fabric of space-time itself, bending light and causing time to slow down near its event horizon. The study of these black holes, and their formation from massive stars like Wolf-Rayet stars, is a crucial area of modern astrophysics. This direct collapse scenario also ties into another important question in astronomy: the formation of supermassive black holes. These black holes, which reside at the centers of most galaxies, including our own, can have masses millions or even billions of times greater than that of the Sun. The origins of these supermassive black holes remain a subject of debate, but it's possible that the direct collapse of massive stars, like Wolf-Rayet stars, could have played a role in their formation. Understanding this process is vital for answering some of the most fundamental questions in cosmology, such as how galaxies and their central black holes evolved over cosmic time. As we continue to explore the mysteries of Wolf-Rayet stars, we are left with even more questions. Despite the advances in technology and observational tools, much remains unknown about these stellar giants. One of the most intriguing questions is whether there are undiscovered Wolf-Rayet stars waiting to be found. While some have already been observed in other galaxies, many remain hidden from view due to their distance, or the sheer difficulty of observing such massive stars in great detail. The advancement of technologies, such as the next-generation space telescopes, holds the promise of uncovering these hidden giants and expanding our knowledge of their role in the universe. Moreover, the study of Wolf-Rayet stars has deepened our understanding of stellar evolution in general. These stars serve as an extreme example of how stars live and die, offering astronomers a laboratory for testing our models of stellar physics. By studying the behavior of these stars, we gain insights into the processes that govern all stars, from the smallest red dwarfs to the largest supergiants. This knowledge, in turn, helps us understand the life cycle of matter in the universe, how elements are created, how stars evolve, and how galaxies are shaped by these processes. Wolf-Rayet stars are, in many ways, the ultimate examples of the power of stellar evolution. Their massive sizes, their brief yet spectacular lifetimes, and their explosive ends make them a focal point in our study of the cosmos. As we continue to explore the stars, the mysteries they hold, and the forces that shape them, we uncover not only the secrets of the universe but also the very origins of the elements that make up our world and ourselves. Wolf-Rayet stars continue to captivate the imaginations of astronomers and astrophysicists alike. While their brief but impactful lives offer remarkable insights into the nature of stellar evolution, they also raise questions that linger in the minds of scientists, pushing the boundaries of our understanding of the cosmos. One such question is related to the specific conditions that allow a star to become a Wolf-Rayet star in the first place. These stars are the result of massive progenitors, those with a mass at least 25 times that of the Sun, undergoing a specific evolutionary path. As these stars evolve, their outer layers are stripped away by intense stellar winds, often over millions of years. This process transforms them into the rare Wolf-Rayet stars that we observe. But what exactly triggers the dramatic shedding of their outer layers? Astronomers know that massive stars typically go through a series of stages, starting as young, hot, and luminous stars. As they age, their cores begin to burn through their fuel at an accelerated rate, resulting in the outward expansion of their outer layers. For most stars, this phase is followed by a relatively calm and predictable death. However, for Wolf-Rayet stars, this is where things take a different turn. The exact mechanism that causes their outer layers to be blown away remains an ongoing puzzle. One possibility is that the intense radiation pressure from the star's hot core, combined with its powerful stellar wind, creates an unstoppable force that strips away the outer layers. Another possibility is that these stars are involved in binary systems, with another companion star pulling material from the Wolf-Rayet star, thereby enhancing the mass loss. This process of mass transfer could help explain the rapid loss of outer layers in some of the most extreme examples of Wolf-Rayet stars. Regardless of the specific mechanism, the outcome is the same: these stars lose most of their outer material, exposing their hot, dense cores. The core itself is made up of heavy elements such as oxygen, carbon, and neon, which are the remnants of the star's earlier nuclear fusion processes. As the Wolf-Rayet star continues to burn through its nuclear fuel, it undergoes massive transformations, eventually culminating in one of the most spectacular and energetic events in the universe: a supernova explosion. Supernovae from Wolf-Rayet stars are particularly noteworthy due to the sheer energy they release. A supernova is a catastrophic event in which the core of a dying star collapses in on itself, triggering a violent explosion that sends shockwaves through space. These explosions are so powerful that they can briefly outshine an entire galaxy, releasing more energy in a few seconds than the sun will emit over its entire lifetime. But what happens next? As the star's core collapses, it can lead to the formation of a neutron star or even a black hole. The fate of the star depends largely on its mass. Stars with masses around 25 to 30 times that of the Sun are likely to collapse directly into a black hole without going through the intermediate stage of a neutron star. This black hole can then exert a powerful influence over its surroundings, attracting matter from nearby stars and even distorting the fabric of space-time itself. Interestingly, the formation of black holes through the death of Wolf-Rayet stars provides a potential link to one of the most enigmatic phenomena in the universe: gamma-ray bursts, GRBs. GRBs are extremely energetic explosions that release enormous amounts of gamma radiation. They are among the most powerful events in the universe, capable of emitting more energy in a few seconds than the Sun will release in its entire lifetime. The exact origin of GRBs remains a subject of active research, but it is widely believed that they are connected to the collapse of massive stars like Wolf-Rayet stars. In the case of long-duration GRBs, which can last from several seconds to several minutes, the leading theory is that they are caused by the formation of a black hole in the aftermath of a Wolf-Rayet star's collapse. The collapse triggers the formation of a supernova-like explosion, which emits a concentrated beam of gamma radiation. If this beam is directed at Earth, it can be detected as a GRB. GRBs are not only fascinating due to their energy but also because they provide astronomers with a valuable tool to probe the distant universe. The light emitted by GRBs can travel vast distances across space, allowing scientists to study galaxies that are billions of light-years away. In some cases, GRBs may even offer a glimpse into the very early universe, providing insights into the formation of the first stars and galaxies. While the study of Wolf-Rayet stars and their supernova explosions has provided a wealth of information about the death of massive stars, there is still much to learn. For instance, the exact nature of the elements produced during these explosions remains a topic of ongoing research. In particular, the role of Wolf-Rayet stars in the production of heavy elements, such as gold and uranium, is still being studied. These elements are thought to be created during the violent explosions of supernovae, as the extreme conditions in the core of a collapsing star provide the necessary environment for the formation of heavy elements through a process known as the R process, rapid neutron capture. This process is responsible for creating many of the heaviest elements in the periodic table, including gold, platinum, and uranium. Understanding the origins of these elements is not just important for our knowledge of stellar evolution, but also for understanding the origins of the Earth and the universe itself. Many of the elements that make up our planet and everything on it, such as the metals in our bodies, the iron in our blood, and the gold in jewelry, are thought to have been created in the cores of stars and dispersed throughout the universe by supernova explosions. In a sense, we are all made of stardust. Moreover, the study of Wolf-Rayet stars and their role in the formation of heavy elements could also have implications for understanding the future of the universe. As more stars evolve into Wolf-Rayet stars and eventually explode in supernovae, the composition of the universe will continue to change. The accumulation of heavy elements in the interstellar medium will contribute to the formation of new generations of stars and planets, further shaping the chemical makeup of galaxies. As our understanding of these stellar giants deepens, we can also expect new discoveries about their role in the larger context of galaxy evolution. Wolf-Rayet stars are not only crucial in the life cycle of stars and planets, but also play a pivotal role in the overall evolution of galaxies. The energy they release through their winds and supernovae can influence the rate of star formation in their host galaxies. This process, known as feedback, helps regulate the balance between star formation and the death of stars. The influence of Wolf-Rayet stars on their host galaxies is also evident in the way they shape the interstellar medium. The gas and dust expelled by these stars enrich the surrounding space with heavy elements, which in turn affects the formation of new stars. Over time, the collective impact of Wolf-Rayet stars on their galaxies may help determine the overall structure and evolution of the galaxy itself. Wolf-Rayet stars are among the most fascinating and enigmatic objects in the universe. These massive, hot stars represent the end stage of a star's life cycle, undergoing dramatic transformations before ultimately exploding in supernovae or collapsing into black holes. Along the way, they create heavy elements, trigger the formation of new stars, and influence the evolution of galaxies. Yet, despite the tremendous amount of research conducted on Wolf-Rayet stars, many questions remain unanswered. The mechanisms behind their mass loss, their connection to gamma-ray bursts, and the specific details of the elements they produce all remain areas of active investigation. As our observational capabilities improve, we can expect even more groundbreaking discoveries that will deepen our understanding of these stellar giants and their profound impact on the universe. With each new discovery, the mysteries of Wolf-Rayet stars bring us one step closer to understanding the true nature of stellar evolution, the formation of galaxies, and the very origins of the elements that make up the universe. These stars serve as a reminder of the incredible forces at work in the cosmos, constantly reshaping and transforming the universe we live in. Wolf-Rayet stars also offer a unique window into the distant past of the universe. Since they are short-lived in cosmic terms, often lasting only a few million years, studying their behavior can provide clues about the environments of the early universe. In fact, these stars may have played a key role in the reionization epoch, a critical period in the history of the universe when the first stars and galaxies formed and began to light up the dark, hydrogen-filled cosmos. The reionization epoch occurred roughly 1 billion years after the Big Bang, during a time when the universe transitioned from being opaque to transparent. Before this period, the universe was filled with neutral hydrogen atoms, which scattered and absorbed light. However, the formation of the first stars, many of which were likely massive Wolf-Rayet stars, began to ionize the hydrogen in the surrounding space, allowing light to travel freely for the first time. Given the intense radiation emitted by Wolf-Rayet stars, they are thought to have been among the key contributors to this process of reionization. These stars, with their powerful stellar winds and ultraviolet light, could have contributed significantly to the ionization of the intergalactic medium. By studying the remnants of these early stars, astronomers are gaining valuable insight into the conditions of the universe at this crucial stage of its evolution. Additionally, the study of Wolf-Rayet stars may help us understand the conditions necessary for the formation of life itself. The elements that these stars produce, such as carbon, oxygen, and nitrogen, are the building blocks of life as we know it. Without these elements, planets with the right conditions for life would not be able to form. The explosion of Wolf-Rayet stars through supernovae releases these elements into the surrounding space, enriching the interstellar medium and making it possible for new stars and planets to form. In some sense, the deaths of these massive stars give rise to the very conditions that make life possible in the universe. As the material ejected by these stars mixes with gas and dust in the interstellar medium, it can seed the formation of new generations of stars, planets, and eventually, life. This cosmic recycling process, in which the remnants of dead stars become the raw material for new stellar and planetary systems, is one of the most fundamental aspects of the life cycle of the universe. It is also important to note that Wolf-Rayet stars are not isolated phenomena. While they are relatively rare compared to other types of stars, they are often found in star clusters or in regions of intense star formation. These clusters, which contain large numbers of young, massive stars, are some of the most energetic and dynamic environments in the universe. The study of Wolf-Rayet stars in these regions provides important clues about the processes that govern star formation and the evolution of galaxies. In fact, star clusters that contain Wolf-Rayet stars are often used by astronomers as laboratories for studying stellar evolution. By observing the behavior of these stars and their interactions with their surroundings, scientists can test theories about the formation and evolution of stars, the dynamics of star clusters, and the impact of massive stars on their host galaxies. These star-forming regions, often located in the spiral arms of galaxies, provide a snapshot of the universe in its early stages, offering a glimpse into the processes that shape the galaxies we see today. Another fascinating aspect of Wolf-Rayet stars is their connection to the cosmic web. The universe is not a uniform expanse, but rather a vast and complex network of galaxies, stars, gas, and dark matter that form a structure known as the cosmic web. The web consists of large-scale filaments of matter that connect clusters of galaxies, creating a framework that shapes the distribution of galaxies and other cosmic structures. Wolf-Rayet stars, with their immense energy output and their role in the creation of heavy elements, contribute to the overall dynamics of the cosmic web. The energy from their supernovae and the material they expel can influence the motion of gas and dust in the intergalactic medium, playing a role in the formation of new structures in the universe. These stars are not just isolated objects, but integral components of the larger cosmic landscape, shaping the evolution of galaxies and the structure of the universe itself. One of the most intriguing aspects of studying Wolf-Rayet stars is their potential to help us understand the origins of life in the universe. As previously mentioned, these stars create the heavy elements that are essential for the formation of planets and life as we know it. But the impact of these stars goes beyond the creation of the elements themselves. Their powerful winds and explosions also play a role in the distribution of these elements across the galaxy. When a Wolf-Rayet star explodes in a supernova, it releases a tremendous amount of energy, sending shockwaves through the surrounding space. These shockwaves compress gas and dust in their path, triggering the formation of new stars and planetary systems. As the material from the explosion mixes with the interstellar medium, it enriches the surrounding space with the elements needed for the creation of new worlds. In this way, Wolf-Rayet stars are part of a larger, ongoing process of cosmic evolution that leads to the creation of planets, moons, and ultimately, life. The very elements that make up our bodies, our planet, and the stars themselves were forged in the hearts of massive stars like the Wolf-Rayet stars. Without these stellar giants, the universe would not be the same. Furthermore, the study of Wolf-Rayet stars can help us understand the conditions necessary for life to exist on other planets. As astronomers search for exoplanets in the habitable zone of distant stars, they are beginning to realize that the presence of certain elements, such as carbon, oxygen, and nitrogen, may be essential for the development of life. By studying the life cycle of Wolf-Rayet stars and the elements they produce, scientists can learn more about the ingredients for life and how these ingredients might be found on planets around other stars. The search for life beyond Earth is one of the most exciting and important endeavors in modern science. By studying the processes that create the building blocks of life, scientists can better understand the potential for life elsewhere in the universe. Wolf-Rayet stars are not just fascinating objects in their own right, they are also key to unlocking the mysteries of life beyond our planet. Wolf-Rayet stars are among the most intriguing and important objects in the universe. These massive, hot stars undergo dramatic transformations, shedding their outer layers and eventually exploding in supernovae or collapsing into black holes. Through their powerful winds and explosive deaths, they play a crucial role in the formation of heavy elements, the evolution of galaxies, and the creation of the conditions necessary for life. Despite the wealth of knowledge we have gained about these stars, much remains unknown. The precise mechanisms that govern their mass loss, the nature of the elements they produce, and their connection to phenomena like gamma-ray bursts and the cosmic web all remain areas of active research. As our observational technology improves, we can expect to learn even more about these stellar giants and their role in the universe. Through the study of Wolf-Rayet stars, we are not just learning about the death of massive stars, but about the very processes that shaped the universe and gave rise to life itself. These stars are cosmic architects, responsible for creating the elements that form the building blocks of planets and life. In a way, the story of Wolf-Rayet stars is the story of the universe itself, an ongoing process of creation, destruction, and renewal that has shaped the cosmos and continues to shape our understanding of the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.